the blackboard, and
Yeah,
this,
I don't see it on that.
yeah,
screen.
that's what I wanted to make sure. Okay, that in that case, I'll improvise, because I thought I'd either use my laptop on which I can draw, or I'd be using the board.
Oh, I have an idea. Maybe what you can do is when you need to write something, you just write on the whiteboard and put the camera to work.
Okay, that's
I think it's the easiest solution. I
Well,
know.
the camera would be very small there because it's shared between things, so they can see.
You're right. You're
I don't
right.
even know how to access that camera.
okay. Either way, when time comes to draw something, we'll improvise in some way. Okay, so thank you very much for the opportunity to give this talk. My talk today is the maximal dimensions of path algebras and graph algebras. As it was mentioned before, this is a project that, at least for me, was born right here, because last time I came to Sydney in November, I got introduced to it, and it was pretty fruitful, thanks to my fabulous collaborators, out of whom I'm not the main one, but I get the pleasure to present our results. So aside from me, it's joint work with Piotr, with Elizabeth, and with Matthew, who is not here today. So, okay, let's go through the plan of the talk. It's pretty short. It will be divided into two parts. Part one is about the general problem for the maximal dimension of a path algebra, and later we will talk about, let's say, a specialization of that to Leavitt path algebra case. So as our entry point to this problem, which at least when I learned of it was the main inspiration, is the result achieved by Hajac and Tomasz in 2020, I think.
But it's a bit confusing, I know.
Yeah.
It's not your fault, but it's not quite correct, because in fact, this theorem was mostly proven by Kivasitu when he visited me, but then we wrote, he published a separate paper in which he had a different version, and then we wrote down this in our paper that it's mostly Kivasitu. So if you want to give
Okay.
credit, it should Tomasz had nothing to do with proving this theorem. If you ask to put the names, it would
Okay,
be
then
mostly Kivasitu.
I'll fix it for my next talk.
In Canada, it's important that it's
Okay, I'll change it for that. It's just that this paper was the one that was cited, and that's why I assigned the authorship.
because it has the original formulation of the theorem.
Okay, so basically, as Piotr mentioned, Kivasitu showed that if we have an acyclic directed graph with non-zero amount of edges, and it has following representation when dividing by the small n, then the maximum possible paths of length k inside of this graph is bounded by this polynomial expression, and the bound was found to be optimal. Unfortunately, I don't remember the optimal graph.
But that's the obvious one. It's why it's called the Cartesian number. Because imagine that you have capital and cards, and you have k players, and then you deal the cards. Oh, yes,
Oh.
we have them. See, we have cards here.
Yeah.
See? you have 52 cards, and you have 1, 2, 3, 4, 5, 6, 7 players. Okay? So 52 is not divisible by 7. So when we deal the cards, there will be a number of people denoted by R will have 1 card more. And then when you multiply it out, because you have, this corresponds to, he has this amount of edges, this amount of edges, and then when you want to count all possible paths, you multiply it out, and that's the number.
So the optimal graph is exactly it.
It's a trunk.
Okay, it's a trunk. Okay.
It's a trunk with as equal distribution as allowed by number theory.
Okay.
So if you go to labeled graphs where you no longer care that the number of edges is an integer, maybe you have square root of 3 of edges between 2 vertices, then this is much easier, because what you do, you divide n by k and take it to the power k.
Okay. Okay, and out of this, the idea of considering not just paths of a prescribed beforehand left length k, but arbitrary paths came about. And so to start talking about this problem in detail, we first fix the notation. So here's nothing surprising, the usual definition of a directed graph, and the usual definition of a path, and what it means for a graph to be acyclic. I don't think we need to stay too long on these slides. And what we'll be interested in doing during this talk is exactly this guy, i.e. the full path algebra generated by the graph E. And when it comes to details, we will be only considering acyclic graphs that have no isolated vertices, because if we allow for isolated vertices, then the obvious answer is infinity. We just take the graph that has exactly an edges and infinite amount of isolated vertices. So to avoid this case, we'll do only that case, and such a graph that is acyclic with no isolated vertices, we call that has the fixed number of edges denoted by big N, we'll call an N forest. If this graph is connected, then it will be called an N tree. And if it has the property that its vertices can be indexed.
Yeah, precisely. Vertices, not vertexes.
My bad. Can be ordered in such a way that the only edges come from the between consecutive vertices, then it will be called an N trunk, and we denote respectively somewhat awkwardly forests by E, trees by Fs, and trunks by T. But fortunately, in just a moment, we'll see that the only thing that are of interest to us are trunks. And because of that, we'll mention that, well, first of all, trunks are really nice to the eye because they have quite easy graphical representation, and moreover, each trunk can be uniquely encoded by its sequence that simply states how many edges there are between the vertices labeled with 1 and 2, 2 and 3, and so on.
And also with combinatoric is pretty nice. Remember, Elizabeth, we figured it out. This is just a high school combinatorics that tells you that if you fix a number of edges to be capital N, then the amount of all possible trunks is 2 to the power n.
Yeah. Although when it comes to this work, it's a tangential fact that is
N minus 1.
because there n minus 1.
Yeah, because for 2 edges, you
very
have exactly 2.
Okay, I'll continue. This is what happens when you present a work to your co-authors. They always say something that you forgot to mention. So coming back to our problem of finding the maximal dimension of a path algebra for a given amount of edges in the graph, the starting point of a trunk is really good, simply because it's rather easy to automate the calculations, at least for the numbers that are still feasible for home computers. And yeah, what I'm showing right now are the calculations for the optimal trunk when it comes to maximizing the dimension of path algebra. And
Sorry, but I don't recall you saying this. I mean, it's obvious to us, but maybe it should be emphasized that the path algebra is just the linear span of all finite paths with concatenation as multiplication. And obviously the dimension of a path algebra is just equal to the number of all finite paths, because you never said that.
oh, right.
I mean, definitely said in Canada.
Yeah, sure.
Yeah, I speak to graphic people, but
yeah, I spent too much time with it and forgot that it's not obvious. Okay, coming back to this this thing, or maybe I'll use the computer to draw. As you can see, there is a kind of pattern that emerges in this data, with the important point being here, i.e. for number of edges greater than 15, everything becomes really regular. And even for the smaller ends, we can see qualitative changes in behavior, i.e. starting from the beginning, starting with n equal to 5. We see that everywhere afterwards, at least 1, 2 is appearing in this data, and starting with n equal to 13. At least 1, 3 appears everywhere, and it is not a coincidence, because the methods that we use to prove how the optimal trunk looks like in this case basically proves all of those facts, that if number of edges is bigger than 5, then it has to have at least 1, 2 in this sequence. If it's bigger than 12, then it must have at least 1, 3 in it. If it's bigger than 15, it must possess at least 2 3s in it. And if it's bigger than 7, then it must have exactly 2 ones at the beginning and at the end. It is, as you can see, not really 100% precise, because here you still have 2 ones, but you also have an optimal graph that only has 2 ones, and same here. You, for n equal to 5, an optimal graph can either be consisting of 5 ones, or it can possess 2. But if we focus only on trunks that have certain presentation, then it is true that starting with 5, the methods that we use to prove these facts are optimal. It's just that the optimal graph can, for small n, be not uniquely determined. But let's go. Oh, sorry. I forgot it's not my computer. Let's go back to the presentation. Okay, I haven't missed a bit. Okay, what kind of machinery we'll be using to prove anything about trunks and graphs in general? Will basically be decomposing the graph into 2 subgraphs on the, let's say that we choose a vertex. Here, the chosen vertex would have index m, and we'll be taking the graphs induced to the left of vertex m and to the right of possibly a different vertex denoted by k, and we'll be analyzing what happens in the induced graph on the left, induced graph on the right, the induced graph in the middle, and the interplay between them. And this is basically the main tool that we'll use to show the formulas for the optimal graph. And basically the only important thing, aside from the notation, i.e. that if we start with trunk E, by E, L, and some index will denote the graph that is induced by the vertices from V1 till Vm-1, and respectively ER will denote the graph induced by all the vertices to the right of a given vertex, in this case with index M, and the important value that we'll be focusing on is the number of paths that end in the sink of the graph induced on the left and that start in the source of the graph induced on the right, and will denote them respectively by L with an index and R with an index. And the important property that these two numbers have is that the sequence of L's is increasing, the sequence of R's is decreasing, and that they both and that L1 is 0 and Rn is 0. The fact that they have to cross each other is the most important step in one of the proofs. So, okay. Another important concept we will be using is the width of A, by which we mean the maximal degree. And what's important is this notation T and W, because we'll see that we don't need to look for the optimal graph inside all forests. We can restrict ourselves to trunks, and then not even to all trunks, but to the trunks of weight at most 3. And yeah, when it comes to first not leaving the world of trunks, the optimal graph when it comes to the dimension of path algebra is achieved among trunks of width 3. Because of time, I won't be showing the whole proof, but basically what happens is that if we have an edge that is, if we have a vertex out of which more than 3 arrows come from, we divide the graph in between these 2 vertices, and we put a vertex in between them and redistribute the edges among these 2 vertices, and it would increase the number of paths.
This is so. Let me wait in for a second. And this was a crucial step. I mean,
Yeah.
This is the point at which this problem started being managed. Because otherwise, this combinatorics was kind of beyond the reach. And also, as a fun remark, let me add that when I asked ChatGPT how to do it, it gave the wrong answer, but it guessed correctly the number 3. I mean, that there will be no more than 3 edges between consecutive processes. But sort of the correct solution, which we have proved, is that you should have as many 3s as possible. As ChatGPT, from what I remember, insisted on having just 1 3 that made one. That's just a wrong answer.
Yeah.
But you know, it was interesting. Also, I don't remember you saying that, and I think it's important. It's not difficult, but it's not entirely obvious. First, you have to prove that if you want to maximize the number of all finite paths given n edges in this finite acyclic connected graph, of course, finite has n edges, it's connected. Then actually trunks obviously maximize it. Did you say it, or did I miss it?
It's the next slide.
As the next slide.
Yeah, because
So I think it's the other way around.
I first started talking about what we did for trunks,
Okay, no,
and that among all trunks, the trunks of width 3
So, okay.
manage. And the next step is that,
but it's especially
Yep.
that you started by referring to the old theorem. Do it in the wrong order conceptually.
okay, then
Because what happens is that in this earlier problem where we fix the length of a path as counted, okay, the difficult part is to show that you're optimized by a trunk.
okay,
Then when you know that it's optimized by the trunk, it's a triviality to see that it must be a trunk like this. This is a kindergarten combinatorics and proved, okay?
okay.
But here it's exactly the opposite. When we count all possible paths, it's really a bunch of simple lemmas to prove that your forests must be a trunk, and then it's best. It's not a big deal. It's not a complete triviality, but it's totally straightforward. But then when we have to look at all these trunks, I mean, we really didn't know what to do. So first we made experiments with Python. Okay, then a breakthrough came with a moment we saw cases only 1 to 3. And only then we have really like dilemmas to prove that among all trunks with width 3, these ones which come up experimentally, this is really the correct answer.
Okay, then I'll change this and I'll put this even before the Python
Absolutely,
calculations, because I put it here because I wanted to talk about the 4 moves that are used to prove it, but we'll behind time, so I'll say only 2-3 words about them, not really even drawing too much of them. We basically use 4 moves that each of them increases the number of paths, but some of them create a bit of a problem, i.e. the first one that splits sinks and sources in obvious way increases the number of paths. The problem is that it can return a disconnected graph even if we started with a connected one. To give an example, if we start with a graph like that, then it will. Thank you, Elizabeth. Then it will return disconnected graph like that. But to come back to the realm of maximizing only among the connected graphs, the 4th move, merging the trunks, provides us with a way to basically glue the sink of one trunk with source of another. And because we assume that there are no isolated vertices, the moment we join at least a vertex and an edge, we get at least the same number of paths as before, most likely strictly more. So it would be 3.
Yes, exactly.
3,
Does it
4,
look okay? Because I can't tell.
like that. So yeah, this is one thing. The other one is resolving alternating paths, and it basically states that if we have 2 paths that cross each other in 2 vertices but nowhere in between, then we can glue the shorter one to the longer one, and combining stray paths. So
I don't know how I messed it up.
we
I'm
have
sorry.
no worries. No. I need the eraser.
Oh, should I go back in? Also, I'm sorry, I messed this up. Do I go to full screen? No, well,
So if we have
full screen
something like this, then we can
and then, okay.
glue
Somewhere
it
here
to
it is. I'll just forget about that.
something like this. That's the resolving of alternating paths. And when it comes to combining stray paths, it's something like this. And we simply erase this arrow from here and change it to arrow like this, and it works. In Beamer, these pictures, at least the way I was doing them previously, didn't look good. That's why I wanted to draw them on board, but I think in near future I'll fix it.
Somewhere there's the view and I don't know. It's unfortunately the HDMI cord.
That is a blue thing, no.
Oh, the blue.
Blue,
Is it
so
the green dot?
green, yes,
Full screen at the very bottom, there.
Okay. So these are the 4 moves that are used to show that the trunks are optimal. And having that, using the in various incarnations, the method of decomposing the graph, we can show that if we start with the optimal graph of weight 3, one of the properties it has to have is that the degree of the vertex has to differ by no more than 1, and that at the very the sink and the source have to have degree 1, and the property that was surprisingly hard to prove was that in such a trunk we have to have a summit, i.e. that there is a vertex. It is even described by the properties of the paths that end in the neighboring vertices and begin in the neighboring vertices. And if we define the index k like that, then for all indices smaller than k, this sequence has to be increasing, and for all larger than k, it has to be, well, sorry, the first one non-decreasing, and the second one is non-decreasing. And because of these three properties, we know that in contrast to arbitrary trunk, which was earlier assigned a sequence M1, M2 up to Mn-1. Here we know that the first couple of these have to be ones, then some twos, then some threes, some twos, and some ones. And of course, the number of twos, threes may be 0 a priori, but when it comes to ones, we need to have at least one at the beginning and one at the end. And out of those three properties, we can reduce our encoding to encoding this graph via 5 numbers, and 1, and 2, and 3, and 4, and then 5. And now the battle is simply to determine what values can these numbers achieve for the graph that optimizes the dimension of path algebra. And to do that, we incorporate, if I remember, 4 or 5 moves that I'll show in a moment, but the summary is right here, i.e. to force N2 to be greater or equal 1, the number of edges in the graph has to be at least 5. To force the N1 and N5 to be exactly 1, the number of edges has to be 8. To guarantee that N3 is at least 1, the number of edges has to be 13. And to guarantee it has to N3 to be at least 2, the number of edges has to be 16 or more. And if we have all these conditions, i.e. if we start with N3 that is bigger or equal than 2, then of course N1 and N5 has to be 1, and N2 and N4 have to be at least 1, then these properties, i.e. those two at the bottom, which say that N2 and N4 have to be smaller or equal than 2, but bigger or equal than 1, and that the difference between them has to be at most 1, determines the optimal graph uniquely up to the mirror image. And how to prove something like that? To prove it, basically, we incorporate 6 different moves. The first one basically takes three vertices that have one edge in between each one of them and combines them into up to the induced subgraph by 2 vertices that have 2 edges in between them. To do that, of course, N1 has to be at least 3, but to increase the number of paths doing something like that, it has to be at least 4. And the existence, the possibility of using such a transformation of the graph implies 2 things. First one is that if the number of edges in the graph is at least 5, then the optimal graph has to have N2 greater or equal than 1, because if we redistribute at least 5 edges into N1 and N5, then we can use this move, increase number of edges, and get a better graph. So starting with the optimal graph, N2 has to be greater or equal than 1. And because to use this move, N1 or N5 has to be greater or equal than 4, it enforces that the optimal graph has to satisfy N1 and N5 smaller or equal 3. And it is one of the easier steps. The harder one is to force N1 and N5 to be equal 1. To do this, we need 4 moves. One is the one that takes one edge from the source to the vertex, and then the one of the vertices where we have 2 edges in between them, and adds this edge on top of them, by which it eliminates one instance of having 2 edges between vertices, one instance of having 1 edge between vertices, and adds a case of having 3 edges between vertices. And this move can be performed if N1 and N2 are bigger or equal than 2, or by symmetry if N4 and N5 are greater or equal than 2. If it happens that N1 is still bigger or equal than 2, but N2, is not bigger or equal than 2, but N4 is bigger or equal than 4, then we can do the same, but still this instance of having 2 edges from the right. And if it happens that we have N1 bigger than 2 and N3 bigger than 1, then we can redistribute the edges in such a manner that we destroy the vertex that has 3 edges in between them, increase the number of vertices having 2 edges in between them by 2, and decrease the number of edges that have 1. To put it simply, we add an extra vertex and redistribute these 4 edges to get 2 plus 2. Okay, and this looks like it's enough, but there is one troublesome case. Well, what happens if we still have N1 greater than 1, but N2 is equal, N4 equal to 1, and N3 is equal to 0? Well, here comes a really tricky move, that takes 6 edges out of the guys that have 2 edges in between them and creates 3 vertices. Each of them have 3 edges in between them. And what's tricky about this move is that we use it more times than we noticed previously. And that's why we have to refer to such an ugly condition for that allows us to use it. But what is really great about this is that if we dig into the calculations, it implies virtually everything else that we need, i.e., if n2 plus n4 is greater or equal than 6 and n3 is equal to 0, then this move increases the number of paths. This enforces that at some point n3 has to be bigger or equal than 1. And in fact, when you calculate it, the maximal number of edges that does not satisfy this condition is 12. So it's exactly the one that we got from our calculations. And similarly, with n3 equal to 2, it's being forced via this move, starting from n equal to 16. So yeah, these are the consequences of just this move. And the consequence of this and the previous 3 that I've shown is that if n is at least 8, then n1 has to be equal n5 and it has to be equal 1. And the last move that is applicable for us is making sort of a rebalancing act, i.e., as long as we have at least 1 3 in our trunk, then we can rebalance the edges with the instances of vertices having 2 edges in between them in such a manner that the difference between n2 and n4 has to always be plus minus 1. And this is what this balancing move enforces. And together with the previous one, it enforces that if n3 is greater or equal than 2, then the maximum of n2 and n4 has to be smaller or equal than 2. So when we put all those restrictions together, it enforces that, okay, if n is at least 16, the endpoint of using all those 6 moves are graphs like that. And they have to be optimal, and the concrete presentation of this graph as trunk depends fully on the remainder of n when we divide by 3.
So why do you have dots instead of commas in your third line there? You have 1 dot.
Oh,
2.
because I made a mistake.
That's
Yeah, that's it. Okay. So this, together with counting the number of paths for these 3 graphs, solves our problem.
Yeah, but we need these formulas for the number. There are 3 systems formulas.
Do we need them? We wanted to find the optimal
Yeah.
graphs.
What is beautiful is that we can really count the number of paths.
Yes, of course we can count the number of paths for them. Okay, I'll
How do we have these formulas?
on the slides, I'm not sure. I don't think so.
It's like the highlight of.
The highlight for me was that we can find
I
the
agree that-
optimal graphs.
I
And
agree
the-
that this is the main
The,
theorem.
the dimension is
Yeah,
just
but what
that-
is it? So tell me the number from a dimension. What is beautiful is that.
if you give me my laptop, I can give it to you. If not, I'm incapable of remembering. Okay, I'll add it.
No, I absolutely don't agree. I mean, of course, this is conceptually the most important thing because that's the theorem. But the point is that quite surprisingly, it gives you an explicit analytical formula, which is even nicer than we get for the Scott-Deck number, which is a combinatorial number, not an analytical number. Whereas over there, just have exponential functions and you see the growth. I mean, here you don't see the growth.
Just one question.
Yeah.
You know, one of the slides that says move 3.
Yeah,
You have this very strange program. How did this come about?
this formula.
I mean,
Okay, this basically comes from the fact that we have a situation that here's some, let's call it G1. Here we have some here should be 2. Here we have this, and I think here was 2, and here was G2. And there was
have different dimensions.
F1,
So
3 edges, and so on. 3 edges, and I think here was it was something like that. And these 2 graphs, they had a sequence and 2 minus 2 0 0 0. And these guys have a sequence 0 0 0 and 4 minus 1, sorry, here and 5. And here it wasn't 1, it was n1. And you compare these 2 graphs, they should be the graphs corresponding to the formula for the move. And when you calculate the number of paths that end here in the vertex that is the last in F1, and the paths that start at the source of F2, and impute it into the formula for the difference of number of paths in the bottom graph and in the top graph, then you would, after some oh, I cannot change the, oh, now it works. Okay, then you get up to algebraic operations, the formula that this minus this has to be greater or equal than 0 for this difference to be non-negative. And that is where this formula comes from. The troublesome part was that when we calculated it, we assumed that n1 is equal to n5 equal to 1. And that is enough to prove these three conditions, but not the condition that n1 is equal to n5 is equal to 1, starting big N greater or equal 8. If you want, I can later provide the detailed calculation, because I have it in my backpack. It was just so troublesome that I just wrote the final case. Okay, I'm well over time, so I'll just say.
But let's go back to this slide showing the trunk. That picture.
This one?
Yeah, thank you. Because I'd like somehow to sum up what you just said, because it's far more conceptual than it appears to be. So first step, as we know, that we have to look at trunks. Then we know that the width of a trunk is at most 3.
Yeah.
Another thing to establish is that the difference between consecutive labels must not exceed 1. It's 0 or 1. So when you jump from mi to mi plus 1, it's just 1 or 0. So it's either the same label or you increase or decrease by 1. And it includes starting from nothing. So this is why the first edge, the first label at the source must be 1, and the last label at the sink must also be 1. And this is actually extremely easy to see that it is the case, because if you have more than, say, 1 edges at the source, you blow it up to the path. And you see that this way you increase the number of paths. And then you starting with 1 is always optimal. By the same token, you see that ending with 1 is always optimal.
Yeah.
Okay. Then so these are the fundamental things there that you have to establish.
Yeah. The next one is the existence of a summit.
Yeah. Yes. Exactly. That you have to reach 3 at a certain point. Yes. Then what we had is
well, not only that you have to reach 3, but that you go only up and down.
I know. So I'm not to say. I didn't say that it's a unique sign. Then we somehow had to argue that there are no valleys, so you cannot go.
Well, that's my point. We don't really we don't argue it, because now it's combined into one fact. Okay. This approach gives it
okay, you must go
in one go, that you must
so
go up and down.
I think, and then we have to say that the summit is as wide as possible, allowed by number theory.
Yeah, and that's what the following 6 moves provide, together with forcing that there's a starting point at which only sink and source can have one adjacent edge, that n2 has to be at some point greater than 0, that n3 has to increase starting from some point. And that is what all these say.
I really would like you to show the 3 sisters formulas.
Okay.
Can you do it somehow?
No, I would need a different computer. Like, I literally don't have it in this presentation.
Are these formulas important for proving, for instance, that your bound is straight?
No, this proves that when it comes to the dimension, these are the optimal ones. The formulas just give you the number for the dimension.
Yeah, but this number
is what you like. Okay. Okay, then
so this explicit formula is satisfactory.
yeah,
from any point of view.
Yeah.
Okay. I understand.
Okay. Exactly. But also, you see, when we were posing this problem, how to compute it, we proved an estimate. We proved with Oskar Sahovic, we proved an estimate for the growth of the number of all paths depending on n. And this estimate is remarkably close to the real number, because for us, we proved that it's bound by the exponential growth at the base of the exponent is eth root of e. And if you compute it, this is 1.444. And here, when you look at what you get, it's the cubic root of 3, which is 1.442. So it's the third decimal point at which it differs. So the estimate, which we did like this by high school calculus, gave us a bound which is so precise when you compare it with the actual number you get at the end of the day. And it has to be a bit smaller because, of course, in order to use calculus, we use this continuous version. So we said, okay, we don't care about integers and things being divisible. We really distribute it equally. The number of edges doesn't have to be an integer. And what would be the maximum number then? And then we got the formula, which is remarkably close to the actual formula. And these formulas show some, remarkable pattern, because you see 3 has a certain power. When you always substitute minus 2k, it's always the same. And the thing which differs is the coefficients.
It comes exactly from
Yeah.
from this. The coefficient comes from the fact that here you have 1, 2, 1, 1.
Yeah.
Here 1,
Yeah.
2, 2, 1, and that's.
But the formulas
that's
get very nice structure. So I don't know. Maybe at the end of your talk, we just pull up our paper from the archive that we showed before.
Okay.
But maybe let's first finish.
Okay. So in contrast to the full path algebra case, where most of the proofs were given using some techniques of decomposing a graph, when it comes to Leavitt path algebra case, the decomposition of the graph is basically used once, because knowing the result that among all n forests, the maximal dimension is achieved for the forest with exactly one thing, we, again, using almost the same method as in the previous case, prove that the optimal the number of paths to the sink among all forests with one sink is achieved for the trunk. And we have an explicit formula for this number. There is a really similar formula for all paths in the trunk. In general, it's unmanageable, but in our case, when we have these optimal, really simple optimal trunks, we can input this data into these formulas and quickly calculate this number, i.e. the dimension of algebra in question. And starting from here, where we have this formula, the modus operandi changes dramatically in contrast to the previous case, because from now, only the fact that, again, we can restrict from all trunks to trunks of width 3. This is the only fact that, again, uses the graph decomposition. The rest of the facts that we use, that we establish, is following strictly from calculation using the formula for PNS, i.e. the monotonicity follows exactly from the formula for the number of paths. And of course, in contrast to previous case where we had a summit that went from 1 to 3 and then from 3 to 1, here we just have the case where we go from 1 to 3.
Sorry, did I miss it? I think did you say that the dimension of a Leavitt path algebra is equal to all paths ending in the sink?
Mm.
When is the limit path algebras equals this when you are with all paths ending in B?
The maximum potential is 3 by graph. Yes, but it doesn't say that it doesn't damage. It still doesn't say that that the dimension is simply equal to the number of all paths ending in the sink.
Yeah, he has this, and then he says that it's optimal for one thing.
Okay,
But you don't-
I get what's missing.
The
Okay,
number of all
let's-
paths ending in, not by pi, okay, it's physical.
Okay.
Not by pi, the number of all paths ending in the.
Okay, I'll write it explicitly for the next time.
Yeah. But
Okay.
somehow this is absolutely important. This is the key to the whole story, and it should be highlighted.
Okay, so again, just as previously, we showed that this difference has to be at most one, and that oh, here's an error. This shouldn't be here. Only that at v1 it's one. And here we have four moves that transform our graph from arbitrary trunk having sequence n1, n2, and n3. After putting it through this machinery of using these moves whenever applicable, we end up with these three graphs that are optimal in the case of maximizing the dimension. And yes, again, I didn't put the number for the dimension. Shame on me. And that is.
There is nothing wrong with this. I love it as well, but there's nothing wrong with adding this one. If you have a wonderful dinner, why skip the dessert?
Because it's too rich.
No, it's perfect.
This gives you all the nutrients you need. It's
Okay.
No, but there's also the taste, you know. So please show the dessert.
Okay, I'm half an hour over time, so terribly sorry for that. And
It's not your fault.
yeah, thank you for listening. Sorry for all the omissions and errors that I made. And if you have any more questions.
Show the.
I feel truly awkward using not my computer. Could you please do it? I'm not.
Yeah.
I'm not used to having to use a mic.
Yes, exactly.
So,
it's easy.
Who would be the next person? Is Piotr, you are the next?
No.
Do you have, are you writing or you are?
I will write, but what I need first to print my paper.
Oh,
It was difficult in the library, so if you could help me.
I don't have an access to print here. Maybe Elizabeth, do you have access?
No, I
Edulon
Yeah.
doesn't work.
Yeah, I don't have access here and I don't have access in the library either. I go to office work. I mean, I hardly print, but
So you go home to bridge.
is there any other way we can? Okay. Or maybe you would like,
I can help to print it.
Yeah.
You know the mysteries of how that picture works.
I don't have access to.
Okay.
Okay, so I
I have some paper.
guess I could write them on top of the board and then they could be projected as one. Let's see. Let me first go back to the first three sisters. Okay. I guess over there. First write them up and then we can do it both sides if you want. And I have to do it for the sink case as well.
It's remarkable that you always have minus 2k.
Right.
I don't quite understand why. And the calculation is not so immediate. And then it's another result, which is important. This calculation is not any more trivial than the lambda solution.
It is way more true.
I would not agree.
I would strongly disagree because you have the formula for all the paths in your graph, and when you put when you insert and 1 and then 2 and then 4 and then 5,
But you don't have a general formula.
of course you do.
Yeah, I mean, once you know the shape of the graph, you can, it's.
For trans you have an
Oh, yeah.
implicit formula,
Okay, yes.
and these are trans of a certain.
Okay, yes,
certain
okay.
form. That's why I thought that the fact that we can get the optimal graph as a trunk of a specific form
Mhm.
is the hard part, because
That is true, yes. No,
because the rest is to apply it to the
Okay,
to the
so-
formula.
And did you
Can you-
finish up the general formula?
Anyone who cares to see, let me see if I can
Yes.
adjust this. So the top formulas have to do with, for me, it appears backwards. That's strange. Does it appear backwards? How do I undo that? Because if people are reading things backwards, that's not helpful. I didn't realize that it did this. Damn.
The second
Hmm.
form of fixed stress, there's no linear term to k.
Yeah.
And the constant one is always
Maybe
minus 1.
settings?
There's another thing which I don't understand how it comes about, what's the rule behind.
Oh, mirror my video preview.
No.
Okay.
Which part don't you understand?
I'm going to
No,
not.
I'm saying that it's not obvious why you have minus 2k always.
Okay, this is where I can at least see correctly. Okay,
Because,
so sorry.
when you
The top formulas are the number of paths in the case where we're counting all paths.
the number and
The bottom are the case where we're only counting paths to the sink. Those are the
In
formulas.
the first case, if I remember correctly, you
If anyone
get,
is, hopefully it makes sense across the internet. Okay, I can just leave them like that.
you get
They're actually
big
visible.
N minus 6 divided by 3. In the second, you get big N minus 10 divided by 3.
Mhm.
And in the third, you get big N minus 8 divided by 3.
Mhm.
And when you take the integer part, from 6 it becomes 2, from 8 it becomes 2, and from 10 it becomes 3. And that's where the difference comes from. It comes directly from to which number the rest of the coefficients sum up to.
But I still doesn't have to explain that they're always minus 2k, because it is not.
These minus ones come from the fact that you are summing up a geometric series. And if I remember correctly, minus,
For a minus 1 by a minus 1, that formula.
yeah.
Oh, yes.
That's where the minus ones comes
Yeah.
from for sure. That's why you have 1/2 over there. And with minus 2k, I don't remember it ad hoc, but it also comes from the procedure where you want to group as much things together with the power as possible, and this comes after. And
Yeah.
because when you have how do you calculate the number of all paths? You take a vertex and treat it as a sink, and you calculate all the paths up to it. And then you sum up for all the vertices. When you have the formulas at the bottom, where you have just calculate everything
To the same.
with regard only to the sink, you get one geometric series, and that's why the minus one come from. And when you sum up sums like that through all the vertices, these minus ones will appear, and they will add up. And I think what should appear here is not 2k, it's k. Because it would come again from the fact that you would have from the geometric series 3 to some power minus 1 divided by 2. And then to put it all together, you have to take another 2 outside. And that's why 2k appears instead of k. The appearance of k would be natural here. Because the k would be the k or k
When you are
plus
taking
1
two common, then there will be 2 in the parentheses inside. the
Yes,
parentheses.
yeah.
Right.
So did I say it correctly? If you have an arbitrary trunk, well, the optimal one. Can you keep the formula for all paths?
stuff.
Yes, but it
And then
would
if you can
be
send
just
the-
as I said.
You're gonna use also key
Start with
transparencies or
taking a track,
No.
use it by the sink,
but
calculate all the
it's-
I need all
calculations.
my black paper.
Yeah.
Yeah,
You're
and
not
then
doing that.
for
Okay.
the path to the sink, you have the.
So it's not
formula
here,
as
it's
well,
in the library?
and you have to just add it up.
Yeah.
Do
And
it
because
here, but today-
for general
We
track,
went to the library.
you would have
You'd have to worry about all the in between.
you will have all the
Exactly.
parameters, it will become unmanageable to calculate, but the moment you plug that you have n1 equal to 1 and 2 equal to 2 and so on, this becomes rather easy to calculate.
All complaints, then it will be.
I also hope you don't mind. I was a little confused. It had it to where it mirrored the input, and my brain couldn't process it, so I turned it off in order to see. But just so that you know, I changed that, and I can change it back if you wish. You had this setting where what you see is a mirrored version of what is
Oh.
actually projected.
Okay.
And when I was wanting to make sure that these formulas were well displayed, I couldn't
didn't
make
even
them up
know- I
myself.
did not even know I had that
Oh,
set up.
okay. Well,
Wow.
if you want to change it back,
No.
good luck.
No.
I can do that for you.
No.
I don't want to change things without your knowledge.
And by the way, there is also a fun fact that if you want to compare asymptotically the number of all paths ending with a sink, the optimal all paths ending with a sink, with the number of all paths, what would be your guess? What is the ratio asymptotically and directly?
Okay. So now, thank you so much. So here you are writing here.
It's slightly bigger than 2. That's
So-
slightly bigger than the 1/0.
There you go. I think this is how we should do it.
Well, you just let this formula and put the limit. Raise them. The thing is that the coefficient that you get is slightly bigger. Depending on which of three systems you compare. It's either 0.2, 3 or 3.3. Yeah.
So this is how it's.
Exactly.
So this is
Exactly. But as you correctly know, it's
sorry.
a false number for any algebra. It's not the dimension, it's the size. So you should square it. And when you square it, the squares are bigger than this one. because we can always put some half algebra.
Maybe you need to write a little bit bigger for the audience. You need to write a little bit bigger. For people.
A little bit bigger.
A little bit
Okay.
bigger.
Erasers
Also, I
here.
can have you not dance around this, my.
Maybe I will. Can I make this pen wider?
Yes,
The line.
The pen is unlikely to make it wider.
I
Okay.
think so.
The line. No.
Let's see,
Thin.
there's definitely
Oh,
something.
it comes back here
Huh.
automatically.
See, does it? Aha, it remembers. Here, look. Whoa, look at that. Well, most
Yes.
of that.
Okay. Okay. Thank you. Or maybe it's too thick. It's,
We can fix it.
no, it will be invisible. What I'm writing. Invisible. Yeah. The shape of this.
I can
But
decrease
will
it.
cause
I think it just, I don't know why it's saying.
something in
behind it.
between.
Let's try that. Click.
Okay.
Is that better?
Much better. Yes. I think it's optimal.
And I'm sorry, I erased your previous.
Okay. Okay. Is
think so.
visible?
Yeah.
I think okay,
Yes.
yeah. Sure.
Okay.
All right, so our next speaker, the pleasure to introduce Tomasz. And I don't have the title here, but it was about outsplitting
Yes, it's about outsplits and
and categorical.
factors and new operation on outsplits
Thank you so much.
based on something which I'm introducing here. This is some structure generalizing the categorical structure, and it is based on the notion of hypercategory. Okay, so the plan is following. So first I'm going to explain the relationship between quivers and Leavitt path algebra. Leavitt path algebras. The second point, I will introduce the notion of a proper base Pasch outsplit.
That's background. That's background.
Okay.
Like a YouTube person.
Okay. Next, I will explain what I mean by quiver morphisms. And finally, maybe not finally, quiver morphisms and and outsplits as ones. Now, I'm going to introduce the notion of a hypercategory. And next, the notion of something which I call recomposition systems. And finally, Leavitt path algebras as functors, as a functor. So, as a functor. Okay. So this is the plan. So let me start. So what is the aim of my work? It is based on the observation that usually, for instance, in algebraic topology or in low-dimensional topology based on links or knots, we can use some combinatorial models to model something which is of topological character. In knot theory, it is about isotopy classes of some configurations of some threads and some links. And for instance, in the theory of simplicial sets, we are using some other combinatorial model to model something which is continuous in a sense, topological spaces. Okay, so the idea is that somehow some kinds of combinatorial structures can encode something which is relevant to homotopy theory. Okay, so this time, instead of usual topological algebraic context of simplicial sets, we will be modeling our spaces, our objects, geometric objects, by combinatorial structure related to graphs, directed graphs, or in other words, quivers. Okay, so the definition of a quiver is obvious. It's a directed graph. I don't have to repeat it. So for me, it's a diagram like this. So in my talk, you will see a lot of lots of arrows, but these arrows are different from arrows used to display the structure of the quiver or a directed graph. So it's a diagram. Okay, so my whole reflection will be about nature of this kind of diagrams. What should I say? Okay, so I hope I do not have to introduce the notion of a Leavitt algebra here. Okay, thank you. So let me pass to the notion of Bates, so-called proper Bates path outsplit. So these are kinds of moves between quivers like this, which guarantee that the induced Leavitt path algebras of these quivers, they are isomorphic. So in this sense, it's an analog of moves between diagrams of links in low-dimensional topology, okay, which we know are generated by Reidemeister moves, and with these moves, we can associate some isotopies between links whose diagrams we draw, which means that this combinatorial information in fact encodes something which is related to something continuous like isotopy. So in the same sense, I'm trying to understand this Bates path outsplits as something encoding some transformations between some continuous objects. Okay, so what is this? So this outsplit is so having a quiver which is as above, such a structure, it's a quadruple consisting of the set of vertices, set of edges, the source map, and the target map. Then let me start my rendering of Bates path formalism in a little more manageable fashion. So first, we start for every vertex. We can associate with this some set of indices, which are the singleton containing 0 if V is a sinc, or it is n tattoo if V is an emitter. Okay, and then we have a decomposition of the fiber of this map S over this vertex. So this is the set of edges starting or emitted from V. Okay, and this is decomposed into the disjoint union labeled by indices from this set IV of some blocks. Okay, such that we have the following properties of these blocks. Maybe I will write it here. So first of all, this block is empty only if V is a sinc. And it is non-empty if V is an emitter. Okay. So this is the definition of this decomposition. Next, something which is called the out-split quiver, which I denote by Q bar, Q tilde, is constructed, first of all, as a disjoint union over all vertices of Cartesian product of this set of indices times this singleton. So this is another way of writing base path labeling of these new edges and vertices. Okay, where new target and source map are defined by the following formulas. And S tilde of I. If E belongs to this block. Okay, that's all. So this is the most general notion of an out-split appearing in the literature. It goes to 2004, where sorry? E belongs to S of sorry. Here S of E. Yes.
I think it's the same mistake.
Yeah. Okay.
Yeah, ISE, Tomasz, not IV.
SE. I S E.
No.
SE.
Yes.
Yes. So this vertex now is the source.
Yeah. Yes.
Okay. Now there's a property which is called properness, which means that for every emitter V, is at most a finite number of blocks okay. And exactly one block
So what is the logical
is
difference
infinite.
between at most finite and finite? What's the logical difference? So
It's the same. It's the same.
Okay.
So this is the stress given to finiteness as a condition. Okay.
We are
Okay.
stressing us.
Believe me, I'm more stressed than you. Okay. Okay. So why this last condition is important? So you should feel that there is some difference between these conditions, which are pure combinatorial, and this condition of properness, which sounds a little bit topological.
That exactly should also be evidence, because it may be.
And exactly.
Yeah, exactly.
uh,
Exactly should be most.
Yes.
But that's the point. You might cannot have more than one
For
infinite
an
block.
wait a moment. What are you? Infinite emitter. So most
For all infinite.
for infinite emitter. Okay, so this is the beginning of this topological flavor given to this combinatorics. Why this properness is important? It is because of the following theorem, due to base and path, that any proper base path outsplit induces an isomorphism of Leavitt path graded
Yes, graded. This is important. It's graded.
graded star algebras. Okay. Moreover, this isomorphism,
Sorry, doesn't read well. Leavitt path graded star algebra.
Leavitt path. Oh, sorry.
Leavitt path graded star algebra.
Grade. Yeah, Leavitt path graded star algebras. Yes.
Or no,
What? So Leavitt path algebra is regarded as a graded star algebra. That's all.
But it looks very weird. Leavitt
And
path
it
graded-
introduces a graded isomorphism.
Yes.
I think the graded should modify.
Yeah, it's an isomorphism in the category of graded star algebras. Okay, so I'm regarding Leavitt path algebra as a graded star algebra. Okay. Moreover,
We think this is star algebra.
there is a very explicit recipe for this induction, namely the vertex V goes to this, and the edge goes to a similar sum. Okay. Okay, so up to this moment, everything was mostly combinatorial, with only one finiteness condition or properness condition, which guarantees that this induces an isomorphism of Leavitt mathematics.
Well, also tells you that these sums are finite, which is false.
Sorry?
These sums are finite because of properties.
Yeah. So properness guarantees finiteness of the sums. Okay. So now we are going to change the point of view. Instead of this cooking recipe for creating this outsplit, we want to understand this outsplit as a morphism between quivers. So what are they? So if you remember, our quiver was a diagram. Okay. So having two such diagrams, I will define
Wrong direction of the first arrow.
sorry.
Wrong direction of the first arrow.
You have the.
Oh, sorry, of course. Razor. So the morphism between such quivers is also a diagram like this. So if you realize that you can describe these morphisms as diagrams, you are tempted to define the composition of these morphisms as pasting of these diagrams. Okay? But this is not choice I'm taking. Okay?
And when you look at this diagram, it's kind of goes without saying, you tacitly assume it's commutative,
Yeah. So all diagrams I'm writing are commutative.
despite we doing commutative.
Yeah. Okay, so
Or diagrams.
this morphism of quivers is something like this. So
So there's a standard morphism of quivers, as
Yes.
the notes from high school.
Yeah.
I find my education is more deficient.
the only non-standard thing is different understanding of composition
Yes.
of these diagrams.
Yes.
Okay, which is different from pasting one or stacking one above another. Okay, why I'm not doing this? Because these outsplits do not form a class which is closed with respect to this stack or pasting.
Yes.
Okay, so my goal is to find some mathematical environment in which we are removing this drawback, and then I will show you to what kind of mathematical subject, in fact, whole subject, this structure is related to. Very surprisingly, this subject is called homotopy theory. Okay, which is surprising because we are in the context of discrete mathematics. But you remember, as I said at the beginning, sometimes discrete mathematics can be used to model, for instance, spaces which are continuous. Okay,
And
so
so
there
there's
is,
the whole, subgroup of combinatorial topology.
yeah, like Hauptvermutung, all this stuff. Okay, simplicial sets, all this stuff uses discrete mathematics in an appropriate way. But this case is different from the simplicial approach. It replaces this simplicial idea by something coming from another corner of mathematics, which is something like symbolic dynamics. Okay, so it's rather dynamical than static, and it is related to some flow equivalences between this in this symbolic dynamics. Okay. So what kind of such morphisms could be regarded as outsplits. So we have the following theorem. Based on, oh, sorry, I need two definitions, maybe one definition for two notions. So the first notion is the notion of a Cartesian square. Okay, so usually they're denoted by a small square inside of this bigger one, and this means that this is a pullback. Okay.
So in which paper did Descartes publish it?
It's Cartesian, but not Descartian.
Just like Leavitt proposed, but that's to Leavitt.
Yeah. So if this square is Cartesian, then we say that our morphism satisfies the target. It's target Cartesian. Okay.
But now seriously, why do you call it Cartesian? I'm just asking for testing.
It's the usual name.
So why?
Because of Descartes. Because Descartes introduced the first example of a pullback.
Okay.
It was the Cartesian product over the finite.
I'm happy.
But next, people started to think about spaces in families. But speaking about families is taking the pullback over not necessarily terminal object. Okay, so everything goes to Descartes. Okay? And second property, which I'm defining in the context of this definition, is the property of a square which is called split. This, okay, so this is a diagonal filler connecting these two vertices of this diagram. And if in our morphism we have this condition fulfilled, then we say that this morphism is, so this is target Cartesian, and this is source split. Okay. Next, I could be interested in properties of these morphisms, vertical morphisms. And these morphisms, by definition, they will be proper. And subjective. If they are subjective, I will call such morphism a cover. Okay? And if they are proper, I'm calling this morphism, so this will be something like this. I will call this this morphism a proper cover. Okay? So this is like a proper cover. Okay? So this was the definition. Okay? And then we have the following theorem. N base pass out split is equivalent to a target Cartesian and source split, but it's not bijective on sinks cover. Okay? And second part is about properness. Under this equivalence, a base pass out split is proper if and only if the equivalent cover is in addition proper in the topological sense now. And
It's about defining.
and bijective on infinite emitters.
Okay, so
Okay. Okay. So we replace these combinatories by diagrams. So now we go further on to the realm of category theory. Yeah?
in my talk, I will use this theorem as a definition of a mass.
Okay. So now, so this is the proof. It's not so important. And we have corollary. So now this construction of the Leavitt path algebra written in this language is like this. Any target Cartesian source split bijective on things and infinite emitters and proper cover induces an isomorphism of Leavitt path algebras Leavitt path algebras, of course, it will be graded and star homomorphism, which is denoted by PQ upper star. This goes from the Leavitt path algebra of this bottom to the upper, to the bottom, to the top, uniquely determined by the following recipe. V goes to the sum over the fiber of this vertex part.
That's the same formula I wrote before, right?
Not exactly. Because now we have replaced this labeling by some indices by something which is purely geometric. So there's summation along the fiber.
Okay, but it's the same sum.
Of course, it's the same sum, but labels are identified in a different manner. Okay. In both cases, so in the previous formula, there was slightly different description. They were not the same. Okay, but now they are the same. It's a sum over all elements in the fiber. Okay, so it's a common formula for this. Okay, so now about composition. Okay, so this composition cannot be performed in the naive structure of a category. Why? Because of this obstacle about this auspicious usual composition if composition of these algebras doesn't work. So to define this, we need some more flexible definition of a category. And this is called hypercategory. So the definition of this notion is following. A hypercategory is a class M whose members are called morphisms. Okay. Equipped with the following structure. Following structure. So first of all, we have a distinguished subclass I in this class, whose members are called identities. Okay. Second, we have an associative concatenation, which means that in fact we are in some monoidal category of morphisms. Generated by two
I'm sorry, but I'm just confused.
argument operation. Yeah?
Okay, a hypercategory is a class M of morphism, so you must
No.
have a category to begin with, right?
No,
So what are they? What
So-
do you mean by morphisms?
we are calling members of this class morphisms.
They have a class and they call members
Yeah.
of the class morphisms. Okay,
Yes.
good, okay.
And we have a subclass whose members are called identities.
Okay.
Okay. Next, we have an associative concatenation of morphisms generated by a two-argument operation, which is denoted by the horizontal bar. So we are thinking about this like a Cartesian product or tensor product here, whatever. We are in some monoidal category. Okay. And so this one must be associative, first of all, like Cartesian product is associative. Okay. And this is also unital with respect to this class of identities in the following sense. Will you remember this? I need more room. Okay, for every morphism, okay, there exists the unique pair of two concatenable pairs no. Too much. Where's this eraser? Whoa. What?
What is snapping?
No, it is not this.
I don't know what was hit.
I hit eraser and everything exploded.
Okay, what if, can I drag it down? No?
Yeah,
Oh, it's
but
darker.
how to make it
Yeah.
smaller?
Oh, I think,
How to make it smaller? Why is so?
I think this was working.
Oh, okay. So your fingers work.
Okay, hang on.
Maybe I have
Let me, is that about where it was earlier?
16.
Is that good?
I don't know. Maybe no, smaller. Okay,
That's too small.
too small.
Yeah,
Is good.
that's perfect.
Okay. To concatenable, I need an eraser. Okay. There are two concatenable, okay, pairs. was okay, of the form, because it's a left and right presentation. So this time it will be like this. And M. I belonging to M. I with I over the bar called a domain. Okay. And I below called called a what? A codomain. Wait a minute. Domain is over the bar is domain, and this is codomain. Okay.
I just found the quote.
So by unicity, which is encoded here in this condition, in particular, we have two maps from M to I over M, and from M to N over I. So this is something like this. M goes to this pair, and this map this I goes to this pair. By this unicity, they are well defined and can be used to define further things. So what are these further conditions? And then we have the relation of composition. Okay? Which will be denoted by this tripod relation sign, which is, I think, is self-explanatory. Okay, so we have something in here, something in there, and then I have the relation with something in there. Okay, so it's a relation between these pairs, okay, and members of this class. Okay, which is, first of all,
by relation, you mean a subset in the Cartesian product of it?
not necessarily. This is a quite general situation. It could be
What the
category. So I said it is not necessarily category enriched in sets. This is the definition, which is as general as in general category theory.
So what is this general category theory definition of a relation? What is a relation?
The relation. Okay, so okay, if they are if these classes of morphisms they come from sets, they are relations in the sense of subsets of Cartesian products. So this will be like a Cartesian product of this and that. Okay. Yeah. Cross this counter domain. Okay. Satisfying the following associativity, which is associative, which means that if I have this, yes, now we apply to the first two things this relation here and identity to this thing. So this will be a relation between these triples and these pairs. Okay? And then we can apply this relation again, and we obtain some relation between these triples and members of this class of morphism. Okay? And we can do something similar, applying first this relation to these two and identity here. So this will go to pairs, and again, by this relation tripod, can be related to members of M. Okay? So these two compositions of these two compositions they are equal as relations between triples and members of M. Okay, so this associativity, unitality, so we say that it's unital with respect to the class I of identities. Okay. In the following sense, that if you have M prime, a member of M, then for every such I over M, the condition that one of these things are in relation, in this tripod relation, if and only if M prime is equal to M. Yes?
I thought you had.
No.
Oh, I.
No? So far, so good.
Yeah.
Yeah. So think as you are in the, try to understand this through the lenses of usual category theory. Okay? And this is the minimal generalization which will be needed for all we are doing here. Okay? If and only if these two things are equal, implying in particular that both compositions of relations, first we go, you remember, we had this map from M to I over M, then we have an embedding of the subclass of identities into M. Now we have equality, okay? And we have similar thing with the role of the domain and counter domain interchanged. So now we have equality here, and we have the embedding of this class of identities into M. Okay, and then we continue. Oh, sorry, I forgot to add this tripod going to M. Okay, and both relations, composition of relations, are equal to the equality relation, or maybe I will write it in this way. Okay, so this is unitality. Okay, so in this language, everything you know about categories can be rewritten If associativity, unitality, blah, 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 everything works. Okay. Okay. So for people not familiar with this formalism, okay,
Which is for all of us.
not all of us, not
All
all
of
of
us. One of people.
Okay. Okay. So I have a good news. Okay. Namely, if we have this hypercategory, so it was the definition of the hypercategory. Hyperdimension. First of all, we can associate a usual category. Okay. So given a hypercut H, we construct something which is called the associated category, which is denoted by C of H, right? And which is equipped with a functor which is a functor from this H to C of H, which is universal with respect to all functors from H to categories. Okay? All functors from H to categories. Moreover, we can associate also with this C of H is groupoid completion okay, which is also equipped with a functor from H to G of H, which is universal with respect to functors from H to some groupoids. Okay?
So this, I don't understand. What are functors into points?
Sorry. So we have a hypercategory and we have a functor.
Yeah, I understand what the functor between categories, but what it means to have a functor into points.
Okay, maybe singular.
So you look at the groupoid as a category and
Yeah.
then
Functors like that, from H to an arbitrary groupoid. Okay?
good as a small category.
Okay, so how to define it? So C of H, first of all, is defined as first. We are taking the free category spanned by this H, because you remember we have this concatenation. So this freeness is with respect to forming these columns of things stacked one above another, divided by the congruence, which is the smallest congruence. Remember, categories essentially is an algebraic structure. So in algebraic structures, we can speak about categories, about congruences, and we can speak about smallest congruence generated, so they're like equations, okay, defining algebra, generated by the following. M1 composed with N2 is congruent to N if they are in this relation, which means this relation of composition. Okay? Okay. So now we are going to this new notion. This time it's not composition.
It's also not
It will be
decomposition.
It will be not decomposition, but it's a recomposition. And this can be axiomatized in an organized way. Okay, so first of all, if you remember, if you have some class of morphisms, okay, we can form such things. Such pairs of such things are called concatenable parts. Okay, and then we have the following definition. So this definition comes with some explanation, some motivation. Okay, so this will be not like definition, this and that is the blah blah that and that. But first, the motivation for this, claiming that since containing invertibles being stable under retracts and satisfying the 2 out of 3 property. Okay, so we are in some. Okay, so we are in some. Imagine that we are in some double category. What is a double category? So double category is like a 2-dimensional thing where you have these horizontal arrows and vertical arrows, and they do not need to be of the same kind. Okay. However, in both directions, we can compose them. Moreover, under this composition, we obtain something like commutative squares. Okay, which means that we can compose these commutative squares. So our hypercategories now will be realized as hypercategories of cells in double categories. Okay, so these are this and that will be cells in a cells in a double. Sorry, So we have these horizontal arrows, these vertical arrows. Okay, these will be proper. This will be arbitrary morphisms of maps, morphisms of sets. Okay, maps of sets. Okay, and now, in such a situation, when we have such cells as members of the class of morphisms, we can speak about some properties of these elements of this subclass relative to the ambient double category. And now let's regard this double category as vertical category of some double category. And then we can speak about, for instance, do these cells, the class of these cells, contains invertible vertical arrows. Okay, is this being stable under retracts? Okay, and the third property, does it satisfy the 2 out of 3 condition? So if you remember, the 2 out of 3 condition is the condition that if you have 1 second and the composition of these two, then if any two belong to this class, the third one must belong to the class as well. Okay, so in particular, it means that the composition, this must be closed with respect to the composition, and yeah, and two other conditions must hold. Okay, but such a situation has some it plays an important role because there are formal properties of weak equivalences equivalences, okay, in Quillen model categories. Okay. Therefore, any class satisfying this list of properties are called, we call it, are called formal weak equivalences.
Sorry, would you allow me to read it? Since containing invertibles being stable under retracts and satisfying the other three properties are formal properties of with equivalences in equivalent categories. Full stop. I don't understand the.
Okay. So now grammar. Any class satisfying this list of properties is called a class of formal weak equivalences. Okay, so this is the cornerstone of abstract homotopy theory introduced by Quillen. Okay. So now we have the following definition of something which is called the recomposition system. A recomposition is a datum consisting of two classes of cells in a double category. Let's say D is above. So there, one, which is called the left class, maybe the left class, denoted by L, and the right class, maybe, and the right class, denoted by R, such that first, L is closed under the, because we are in double category, we can compose vertical things under the vertical composition. And two, and at this point we are quite flexible because R is closed or maybe co-closed under vertical decomposition. So what is decomposition? decomposition is a dual analog of composition. So having one thing, we can decompose it, and this decomposition is co-associative and co-unital. So although this vertical composition is inherited from this double category, the new datum here is this decomposition, which must come from elsewhere. Okay? Moreover, both these classes, both being formal weak equivalences, with respect to composition and decomposition respectively. Okay? Respectively. So, okay. So these are this first condition with 2 points. And the second condition, the second bullet, is this structure consists of the class, maybe A class or A class. S, no, it's because everything is already meaningfully determined. So it's the class of spans L and R, with L belonging to L and R belonging to R. Horizontally, no. So maybe different. So let's speak first about L. So first of all, L is directed horizontally to the left, and R weak, and R belonging to R directed horizontally to the left, to the right. Okay. So this classes is like this. So I'm thinking about this like this. So this is the span. So you see that this reproduces the structure of our outsplit. Okay. So the motivation for this notion is our outsplit understood as a diagram.
So you use the pullback squares as your L.
So this belongs to, so this is L,
Yeah.
and this is R. This cell is L.
But the composition of pullback does not satisfy the 2 out of 3 properties. Right?
No. But you remember, these, they are proper.
Yeah.
Objective, and then it satisfies.
Oh.
There's an article. It's not published because it's a note by Marcin R. Przybyłek. It's a guy from my university who wrote a paper entitled "The Other Pullback Lemma." So this is exactly about your question. This answers your question. Okay. So in our situation, they satisfy this 2 out of 3. Okay. Okay. So this is recomposition system. Why they are so interesting? Because of the following proposition. It's not a big theorem, but it's good to realize this. for every recomposition system, the datum consisting of, first of all, the distinguished class, subclass I, consisting of spans of vertical identity cells. So these are cells where both vertical arrows are identities. Okay, so this defines this class I of vertical identity cells belonging to L and R, respectively, and the relation I have to introduce somewhere this class. Okay, so this S is a part of this structure of this recomposition system. So this relation denoted like this, where and now we have pairs L2 R2, L1 R1. We have this relation with a pair LR, and this holds if and only if we have this condition on this relation composition or compositional relation between this and that. And then I'm introducing something interesting, where here this, I will describe what is this, but this datum makes the above class a hypercategory. So this comes from the composition in this recomposition system, and this is the relation which by definition is transposition of the composition. Okay?
Of the transposition of the composition is recomposition?
No. Recomposition consists of these two.
Of these two.
For this left class, or this right class. So on this left class, you have usual composition. And on this right class, you have the transposition of the composition. And then I will show you an example coming from the context of base path outsplits. Okay?
Now, may I have a formal suggestion for keep some app on time? Because we cannot explode to midnight.
Tomasz, you had about minus 40 minutes.
Okay. Counting from what time?
Now, minus 40 minutes.
Okay. Okay, good. So this is about this hypercategory. So let me explain here what is this, what is not this transpose of the decomposition. Definitely it's not composition in the example. Okay, so what is this example? So I'm finishing. So what is this example, it is something like this. So if I have no, if I have not in this direction, undo. Okay, if I have this right class like this, okay, so these are diagrams corresponding to split. So this is this right square in the sense of the outsplit, okay? And now we have the following. We define this relation okay? Using not the composition of these two squares, because it doesn't make sense. If you have these two splitting condition for these two squares, there is no way you can combine from it the splitting for this naive composition of these two squares. Okay, so this is this difficulty which makes this outsplit not being close with respect to this naive composition. But what is this recomposition? So first of all, this recomposition is like this. I cannot control this. So first of all, I'm splitting this. Okay? And having this diagonal filler here, green, I don't know.
I think somehow like your finger brush and then it.
Maybe I have green fingers. Okay, so look. So from this, I'm going here in the opposite direction. So this is the decomposition.
Wait. Now he's not touching it.
I don't know. I don't know. It's magic. So what I'm doing? So first of all, look, if I have this, I can compose these two, which makes me this one. From this. Okay?
Yes.
So this is this one. I can compose this with that.
That is correct.
Which makes me this. And I can compose all three to create this. Okay? It's very simple. It's very simple. Nothing strange, no axiom of choice. It's purely coalgebraic structure. Why coalgebraic? Because this is coassociative and counital. Okay? So this leads to a hypercategory. Because if, of course, we can prove that this is this recomposition system. So we have to check all these properties. Of course, it's not difficult to see that isomorphisms are contained in this class. What is difficult? To realize that all this business with retracts, okay, and 2 out of 3 properties make sense for all properties of an outsplit. Okay, you remember what was this? So outsplit was target Cartesian, source split, bijective on sinks, bijective on infinite emitters, and vertical arrows were surjective and proper. So I have almost 20 lemmas, okay? When I'm checking all these properties, okay? So if this is a hypercategory, so this leads to this groupoid, associated groupoids. Okay, and because of this explicit formula for the morphism between Leavitt path algebras, Leavitt path algebra, and of course this universal property of these functors, okay, Leavitt path algebra is what? Is a functor from the this groupoid of this hypercategory of outsplit because of this mixing of this algebraic composition of these left arrows. Because for the left arrows, so these are like this, okay? You have usual composition. So this is of algebraic structure. For this, you have this coalgebraic structure, and you are reversing formally, changing the direction of arrows, like we do in defining the convolution algebra structure, built with a coalgebra and an algebra. Okay? Therefore, we call this outsplit convolution hypercategory, and this will be called outsplit convolution groupoid. So it's outsplit convolution groupoid. And this is a functor to the groupoid of graded algebras, algebras. Okay? So,
how does it relate to this canonical groupoid of these paths?
No. This is the groupoid as a whole category. It's not a groupoid associated with a single quiver. It's a groupoid of all such quivers with very complicated morphisms between them. Okay? So the last question, there's an open problem here. Since these morphisms here, they behave like formal weak equivalences, so the question is following. Open question. Is there a model, or Quillen model, Quillen type, model hypercategory, of course, in which base pass out proper outsplits are weak equivalences, because they resemble by their properties, they resemble weak equivalences. Equivalences. Okay. Yeah. So this is this question. If so, what is this? Sorry. If clean all.
Yeah, so
How to undo? No. Clean. Undo. If so, hypercategory, I don't know. Let's call it like this. Okay. So the localization or homotopy. So localization with respect to weak equivalences is called, what I'm doing.
It's not realistic.
Yeah. Okay. So the homotopy category, which is the localization of this model equivalent category with respect to weak equivalences, the homotopy category of this should be a genuine domain for the Leavitt path algebra construction as a functor. Okay? And many other questions like this are in order. Okay? What if we replace outsplits, for instance, by other moves? With, no, for instance, in-splits. So instead of isomorphism, instead of this groupoid of system algebras, you obtain a double category, maybe not double, bicategory, okay, of algebras and bimodules as one morphisms, okay, and so on and so forth. There are many questions in this spirit which can be asked here, but the main point here is that thinking about these combinatorics along the lines of this homotopy theory, we could explain why is it so. For instance, if we have classical spaces and we quantize these spaces, deform quantize this space or quantum deform these spaces, okay? Many of them happen to have this combinatorial model of type of this graph system algebra, okay? And the K-theory of this is, or at least K-theory groups, are the same as classical K-theory of spaces before this quantization, okay? So it's quite possible that this is the pathway to some conceptual explanation of this problem, okay? Because it's very hard to understand why even it could be possible, okay? Because classical spaces can be modeled, for instance, by simplicial sets like spheres, whatever, okay? Projective spaces, Grassmannians, what else? There are many such lens spaces, yeah. Real projective spaces. Many classical spaces can be quantized, and it turns out that the K-theory becomes additively the same. So it's it's very difficult to understand why, because this is very non-trivial situation. Because if you remember, Piotr, for instance, our paper about what is happening in the classical limit. Classical limit is singular.
Oh, you mean our CMP paper, right?
Yeah. So it's singular. What is happening there? For instance, you can have K-theory, which has geometric generators. But after quantization, this classical generator doesn't make sense. But they appear new kind of generators related, for instance, to the presentation as this graph system algebra. Okay, but there is no obvious relation between these two sets of generators. Okay, so because this in this limit, not only K-theory, you can speak about cyclic or pairing between cyclic homology and cyclic cohomology. Okay, so if you have some geometric generators of K-homology and you have some classes in K-theory, and if you go to this classical limit, what is happening? One in this pairing goes to infinity, another one goes to zero.
But they still match up.
But the pairing is constant in this family. Okay?
And it's not something wild. I mean, you get it at the simplest example.
Yeah.
Like what they steal.
So, but again, so generators depends on geometry, which is very rigid. But this pairing is fully homotopic. So this can be explained on the level of homotopy theory on one side of spaces, on the other side of operator algebras. So up to homotopy, everything goes smoothly. Anything which is homotopical, homotopically invariant goes smoothly through this classical limit, which is not the case of geometry, classical geometry. So something can happen here, because in this classical limit, geometry disappears. This geometry of kind of this simple simplicial models of spaces. But there is some flip to some other combinatorial model, like, for instance, this C-star graph algebras. Okay? It's a different kind of combinatorics, which reproduces the same homotopical information. So therefore, putting everything into the common homotopical language of Quillen categories, maybe, this is a long shot, okay? But maybe at the end of the day, it could explain what is happening between this, let's say, quantum mathematics and this classical mathematics, okay?
Tomasz, just to wind it up, would you go back to the previous slide? No.
Oh, no. Previous.
Yeah, I just really want to understand this last line. So in what sense Leavitt algebras are give me a factor? So I have the G of H, which is G of H is a groupoid?
Yes, it's a groupoid, yes.
So it's a small category. Blah, blah.
Yeah, okay.
It's a groupoid, and this is a groupoid that you obtain out of this hypercapital.
Yes.
Okay.
So this means that even here, even on the level of associated usual category, already morphisms are not on the nose. They are not these diagrams. They are classes of these diagrams with respect to this smallest congruence.
Okay, so in this point, which is a small category, what are your objects?
They are quivers.
Quivers, not classes of quivers.
No. These are quivers.
These are quivers.
Classes are all. So look. So this is a good comparison. It is like homotopy category. So therefore, at the end of the day, this open problem is phrased in terms of this homotopy theory, because homotopy category usually gives you the category with this. If you have a usual category, model category, then you have these weak equivalences. But if you invert formally these weak equivalences, you obtain homotopy category. So objects are classical spaces, let's say, but morphisms are classes. Okay.
Okay. Now, it's becoming more clear. So now, what is this groupoid of graded star algebras? What is the groupoid of graded star algebras?
Objects are graded star algebras and isomorphisms between them. Yeah.
Classes of isomorphisms, or isomorphisms.
No. Isomorphisms. Not classes here. Classes are there. So combinatorics goes through this homotopy-like business. But here we have algebra, nothing more.
Okay, so you are saying that you get the following picture. I have, say, a quiver,
Mhm.
and then I have an equivalence class of outsplits
Yes.
to another quiver, or another bunch of quivers, or a quiver.
No, to another quiver. Objects are quivers.
Okay.
Simply.
So I have a class of outsplits to another quiver, and this is already for me tough to digest, because when I fix two quivers, is it there little many outsplits in between them? Possibly yes. Okay. Okay, and then I assign these Leavitt algebras to them, and you say that to every element in this class of outsplits, I assign one and the same graded star isomorphism.
Yes. Yeah.
One and the same.
Yes, yes.
Okay.
So here is an algebra. So in the sense, Leavitt path algebra is an invariant of this homotopy category.
I'm happy. I'm happy. So let's move on. Because it's. Yeah, this is a very beautiful take on this.
But constructing this higher, this wider category of equivalent type model category, model hyper.
Hypercategory, this is not a standard notation. This is something you introduce hypercategory here.
At this level of detail and elaboration, it's mine.
Right.
But people were using these hypercategories as categories enriched in the monoidal category of sets with relations instead of set theoretical maps. Small.
So while we are setting up my slides, there's a song about hypercategories that I want to play for you.
Sure.
Hyper.
It looks like that.
Oh yeah, I will go here.
Okay.
I will go here.
Yeah.
Ostatni raz, teraz Hajac fondację, wyliczałem wzorek, żeby wsadzić do Kanady. Ja po prostu podam ogólny wzór na to, ile to wynosi zawsze i podstawię, bo to naprawdę jest.
Wychodzi 42 i wszyscy to przyszli.
Właśnie chyba wyjdzie 253, tak jak tam.
Ja wolę 42.
Ja szczerze mówiąc,
Oh, this is my mind.
Just having a quick look.
Look at this 20 levels.
Right.
40 pages of very simple calculations. But the point is that they work, which is quite unexpected.
This one I really like. This one.
This
This is very
This is
nice.
nice.
Yeah, this is very nice.
By the way, in the equivalent model category, this split, maybe not this, but split squares, they are part of the structure. Because in this model category, you have weak equivalences, you have co-fibrations and fibrations.
Right.
And one class is defined by another class by the property of the existence of this diagonal lift, of diagonal filler. The same as on the right hand side of half split. Okay, so so my feeling is that it's not an accident. It's not an accident. And what is also nice, if you remember, there's base path definition of this partition being proper. Okay, and this is related to proper maps. Okay, there is the notion of outsplit, and this is related to split squares. Okay, so people forming this lingo in this subject probably had right intuitions how to choose names for these things, but I doubt if they understood how much they are, how far they are right. Sometimes it's some phony goal. Of terminology. Phony etymology. Okay. If you like some things,
Yeah, and they just put some.
yeah, but this is not the case here. Everything
Matches.
matches.
All right, very good. So we really don't have that much time. Yeah. So
The size is kind of wrong.
How to minimize it? Not. Maybe smaller. I know that when I touch the screen, something wrong. So that
And it's why the green was.
I'm not going to even try to help.
Oh, is it? Is the
That's completely exploded.
Somehow it seems a little off. Let me go.
Completely green. It's completely off, not a little off. Because I think.
Okay. And then let me go to here.
It should fit.
This. There we go. And let me. Pi. Who is pi?
Oh, thank you, Elizabeth. That's
I think it's like the people I know that are tech savvy that help me and how I am sorry that I am all that is a different.
Can I write on the slides here now?
This button here, I think it should be visible to you here. And I think if you, well, let's see, hang on, this. And if you choose that pen and pen, and I'm pretty sure that should be visible
wonderful.
to everyone. So this is very crude. This is just you drawing with the mouse pad.
Yeah, but yes.
Yes, and I'll clear it.
Yeah.
Clear all drawings. And I'll let it go back.
Yeah.
Oh, wait, not.
No, this bar can stay.
Oh, okay. So pen.
Yeah.
And I'll just leave it there.
Yeah.
But this
I will
should
not need to
still,
write much, but like Łukasz, I need to show.
hang on just a sec. Let me make sure that you can still, it might actually have to be, because I'm trying to, it didn't seem to be working with this in the meantime, so maybe you should leave it off, but if you want to use it, you can click on that. Sorry, just because I forget it again.
Działało przez 100 lat.
Mniej więcej na stulecie to jest wprowadzanie. No ale wprowadzanie dlatego, że tracili bardzo udział w rynku wśród najmłodszych. Tak. No Presley w tamtym czasie na przykład zainwestował w to, żeby ich tak samo był Michael Jackson. Porki.
Widzieliście się na tym nabierali?
Znaczy wtedy jeszcze nie miał żadnych spraw, więc nigdy niczego
Jeszcze-
nie udowodniono. Nie udowodniono. Nie ma go tak jak Epsteina.
there we go.
Okay.
A mam go.
I just do also the video on. Where is the video? I think we are set. All right, so our next speaker is our very own Piotr. He's going to tell us about classifying admissible graph homomorphisms and factorizing outputs.
Thank you very much. Let's rock and roll because we are way behind the schedule. Oops, and now the point is always you have to click something. Okay, it works. So, of course, I'm not going to define graphs or Leavitt graph algebras or graph sister algebras, but I really want to make sure that we are on the same footing, and I will remind you what I mean by morphism of graphs. So, Tomasz already gave you one concept, which is here a special case when we preserve a length. This is the same. So when I have a morphism of graphs, I view it as a set theoretical map between the space of all finite paths in one graph into the space of all finite paths in the other graphs. And for the time being, we assume that vertices are mapped to vertices, that you preserve start points at the end points of your paths, and that you have this beautiful concatenation property. So if you can concatenate P and Q, then f of P and f of Q are also concatenated. Okay, and
So this means it's a fun.
Exactly. Yes, it means it's a funct. Yeah, yeah. If you want to put it very succinctly, when you view a graph as a small category, then this morphism is just a funct. But in order to get into what you were giving as a morphism of quivers, then you have to also demand that it preserves the length of paths, which means that edges go to edges, and not that edges go to vertices or that they go to paths, which is a very natural thing happening in real life of noncommutative topology. We didn't do it for the sake of generalizing. I mean, the moment you start to study examples coming from noncommutative geometry, quantum groups and so on, you must forfeit this assumption of length preserving. So you must forfeit the grading, you must forfeit the U1 equivariance of graph sister algebras, okay? And so this gives us two ambient categories. One will be the category of path homomorphisms, one will be the category of graph homomorphisms. But what we are interested in appropriate subcategories in these categories that have functors into algebras, or if you want, sister algebras. And if I look at graph homomorphisms, okay, then I can produce three conditions that allow me to have a contravariant functor into U1 equivariant sister algebras, that's star homomorphism, U1 equivariant star homomorphisms. On the other hand, if I put appropriate admissibility conditions for path homomorphisms, this gives me a category with a covariant functor into sister algebras and star homomorphism, but this is no longer U1 equivariant. So the gauge action that you have automatically coming or Z grading with Leavitt for Leavitt of algebras, it's no longer there. Yeah, okay. All right.
Could you expand this?
What?
Shorthand, this notation, HA.
Oh, you the acronym. Yeah. So admissible graph homomorphisms, admissible path homomorphisms. Okay. Yeah, I mean, used to have some monstrous names for it, but it looked like a genetic code, so I decided to simplify it. Okay, and then as many of you know, you can unify these 2 points of view, have relation morphisms. Then we can go to extended morphisms. There's a lot of stuff going on, but today I really want to focus on some very simple things which we just obtained, but that's just a quick preamble. So now we have a category of sister algebras or U1 equivalent sister algebras and U1 equivalent star homomorphisms. And now how do you have this U1 structure on a graph sister algebra? Well, you can take any edge, you can take the corresponding partial isometry as E, and you are simply rephasing such partial isometries by elements of U1, all the time same element of U1, and you keep projections invariant. And this, by the universality of a graph sister algebra, it gives you a nice continuous U1 action on a graph sister algebra. Okay, so this is the way in which to a given directed graph, if you assign a graph sister algebra, you actually land in the category of U1 sister algebras, because the thus defined gauge action makes every graph sister algebra a U1 sister algebra. Okay, and now here I have these two functors, and maybe let me explain. It's not like we worked with Katsura, but it turned out that Katsura discovered these admissible graph homomorphisms in the more general context of topological graphs like 10 years ahead of us, because we're not aware of it. We rediscovered it in this discrete context, but everything agrees on the nose. If you put discrete topology into Katsura, you get on the nose what Mariusz and I derived. And the big take here is the following, is that whenever you have an admissible graph homomorphism, then by the formula, it is exactly the formula Tomasz was writing. This is the same formula. And this is why you need properness so that the sum is finite. Because here, even though you are in this hysteralgebras, it's not convergent in any norm. This sum has to be finite. Okay? And this defines a U-N equivalent star homomorphism, which goes from the graph hysteralgebra of F to the graph hysteralgebra of E. And you get this contravariant functor from AGA, AGH to U cal. And let me mention here that in addition to the equivariance, we have another nice property which is not shared by the other functor. And notably, if your algebra happens to be unital, which happens when the set of vertices is finite, then this star homomorphism between unital hysteralgebras is actually unital. This is no longer true below. Okay. So the other functor, which is now our baby, meaning Mariusz and myself, if I have an admissible path homomorphism, so this is what Elizabeth will unravel, then even a simpler formula, which is simply saying that I have my partial isometry in some more general sense. It can be a projection, or you can also take it a path if you want to. That phi star applied to this partial isometry is just S of phi of P. Okay, and this defines now the star homomorphism from the hysteralgebra of E to the hysteralgebra of F. So note that this is covariant. Okay. And you have a covariant functor from admissible path homomorphism to hysteralgebras. You obviously lose equivariance because when you don't preserve a length of path, so you see, even if this is an edge, this can be a path of like million, or it can be a vertex. Okay, so obviously you screw the grading, you screw the equivariance. Okay, but in real life you have such maps in noncommutative topology, and examples coming from quantum groups. Okay, if you want to relate a quantum disk with a quantum real projective space, voila, you have maps like this, but they're not equivariant. Okay. But there's another important effect. Even if you have finitely many vertices in E and finitely many vertices in F, which means that these graph hysteralgebras are unital, this star homomorphism need not be unital. And the prime example is, say, the construction of compact operators. When you include smaller size matrices in bigger size matrices, you include them by enlarging them by 0, so you map a unital hysteralgebra to a unital hysteralgebra, but your map is not unital. There's no unital map between matrix algebras of different sizes. Okay, so that's if you want the background. Sure.
So of course, this free category of finite paths is generated by elements of degree 0 and 1.
Yes.
But these homomorphisms, they extend to paths of arbitrary length.
Sure.
What is this extension? How?
I mentioned it. I mean, here, you see, here, it's okay to take any path. I could just say that P is a path, and that phi star of S of P is S of phi of P.
Okay,
you can.
So for this covariant,
yes,
it extends to arbitrary paths in the same way.
Yeah.
What is happening for this contravariant? Do you obtain some cross terms?
Yeah, exactly. Exactly, because if you write the path here, then it will be f of s E1, E2 up to En, and then you'll have to multiply out these sums. Yeah, so this is what will happen. But the reason why we are a little bit careful here comes from relation morphisms, because when you try to get your functor for relation morphisms, what we first tried with Gilles is exactly like we can do here. Let's take paths and everything should work, and we got wrong formulas. When you do relation morphisms and you define a functor, you really have to stick to vertices and edges. But it's too long a story, and it's not part of my talk. Here it's okay. You can take P to be a path. Yeah. All right. Because I will classify all admissible graph homomorphisms, I'm not going to define what it means to be admissible because the classification will sort of answer this question. But to help Elizabeth with her talk, let me unravel a little bit at least of what we mean by admissible path homomorphisms. So first two conditions are very easy. When you have its injectivity on vertices, okay? So you must be injective on vertices, and kind of if you look at this formula, it's totally obvious. If you have mutually orthogonal projections, you cannot identify them. Otherwise, you would kill the homomorphic property. And this condition alone allows you to have a map between path algebras. Just this condition alone would give you a functor between path algebras. Now, if you would divide by the first conscriptor relations and would like to have a map between associated compact algebras, well, then you have to have this condition and that one, the monotonicity. Well, it's also very easy to phrase because it says that if I have two finite paths that are mapped to comparable paths, and now this is, now I need to write a little bit. I click on this, I choose a pen. Okay. Okay. And I say that the path alpha is comparable to a path beta. When I have that beta, it's not a touch screen, no? It's not a touch screen because it's in Macintosh. Okay, this is what I don't like about apples. Where beta is an extension of alpha. Yeah, it's horrible. Now it's impossible to write with this.
I can try and see if I can make it work. Erase. Erase. And then hang on. And beta equals.
You could type. Look, you have the option of typing.
Hang on. Alpha.
Gamma. Yeah. So
or some gamma. I'm
yeah.
not going to write that.
Exactly.
Or something.
Exactly. Or the other way around. Okay. So this is beta is an extension, but it's important. You always extend to the right. This is why I wanted to write the formula. Okay. So either beta is extension to the right of alpha or the other way around. Alpha is the extension to the right of beta. When it happens, we say that these two paths are comparable. And a monotonicity means that if two finite paths are mapped to comparable paths, then they themselves are comparable. Okay. We have many formulations of this monotonicity principle, but this seems to be the easiest one. And now comes, oops, sorry, now you have to. Yeah, but it's I cannot. Okay. And now we have a regularity condition, which is quite tricky to explain, so I'll leave it to Elizabeth. But you can view it as a combinatorial formulation of a second Kunst-Krieger relation. And you really have a full equivalence. Notably, you can say that this regularity condition, which we impose on already injective on monotonic path homomorphisms, is satisfied if and only if the induced map between path algebras preserves the ideal generated by the second Kunst-Krieger relation. So this is really equivalent to the second Kunst-Krieger relation. It's not only that it allows you to satisfy the second Kunst-Krieger relation, it's actually equivalent. So you cannot have any lesser condition. Okay, by law, I have to put this. And now you're right, Elizabeth, I should clean this.
What is condition?
Oh, I'll get that.
Yeah.
Trash can.
Should I do it?
Yeah.
And then for your drawings, that popped up when you do that. And then, yeah.
Okay, done. So I'll just kill this. Okay, so yeah. What?
Yeah, my question was regularity is a combinatorial.
Yeah, but it's very complicated. I leave it. I leave it. Elizabeth.
You don't want to.
I don't want to do it. This is for her talk. This is for her talk. Yeah,
Okay.
yeah. Okay. So now, in order to somehow make sense of this classification of admissible graph homomorphisms, It turned out to be very handy because you classify up to isomorphism anyway. It turns out to be very handy to introduce the concept of the standard graph homomorphism. And you see the way we do it is the following. We take an arbitrary graph as our target graph, as our codomain graph. The E is absolutely arbitrary. And now we try to construct an admissible graph homomorphism into this graph. Okay, so we start by having an arbitrary vertex map. So I have some set E pi 0, and I have a map, the usual old-fashioned set theoretical map into the set of vertices E0, the vertex map. But now when it comes to the set of vertices, I define them in this new graph, in the domain graph. I define it as the fiber product of two maps, the target map and the pi 0 map. So in other words, these are all pairs of edges in the target graph and the vertices in the domain graph, which are compatible in the sense that the target of E is equal to pi 0 of V. Okay, so this is exactly how I have this Cartesian square. And by the way, this all came from people doing things like maybe topological graphs and so on and so forth, because both Katsura and us, when we looked at this condition, it was written in the form of target bijectivity. You can just phrase it in a very, theoretical sense way by saying that the target map, when appropriately restricted, will give you always a bijection, But this was again a bit like a cooking recipe. But I repeat, both Katsura and us, we did it. But then Mariusz was in Arizona working with John Quick, and they did some more general graphs. As they're doing these more general graphs, they were using this Cartesian square property. And when I came to Arizona, Mariusz told me, look, maybe we should do it like them. He said that we have a Cartesian square, not that we have a target bijectivity condition. And is of course completely equivalent, and this is how this construction entered the game. That we realize that in fact the set of vertices in the domain graph, it must be a fiber product construction. There's no other way. Okay, because it's something that enforces monotonicity. You see, the condition. Sorry, no. What am I saying? No. That's the target bijectivity condition that was derived by Katsura and us. It's by reverse engineering when you want to preserve a first Kunstkrieger relation. So you have a map, you have a formula. And then you ask yourselves, okay, so now what should be the properties of my graph homomorphism that the first Kunstkrieger relation is preserved? And when you unwind it to the reverse engineering, you realize that this is this target bijectivity, which basically means that if you identify two different edges, it might happen only in the case when these two different edges have two different endpoints, and you also identify these two different endpoints. And you have sort of a bijectivity between the set of edges that you identify and the set of endpoints which you identified. This is why it was baptized as target bijectivity. But a far neater way to do it is by saying, hey, we have a Cartesian square. Okay, and then I define my pi 1, so my, if you want, edge map to be the canonical projection of the first component. And I define the target map for my new graph to be the canonical surjection onto the second component. And now the only thing to really have a graph, E pi, I need to choose some source map, S pi, okay? And I assume that there exists a map, S pi, which is the source map to be, that intertwines pi 0 and SE, where SE is the source map in the target graph, okay? This gives me a graph E pi, and of course I have these commutative diagrams, which is exactly like what they have in Tomasz, except that I have S on the left and T on the right. And because these diagrams are commutative, that's the definition of a graph homomorphism. So this way we obtain a standard graph homomorphism, okay? Good. And now you have this classification claim, which is remarkably simple. And this is what we did with Elizabeth right now after I arrived. So this is like 2 days old. We did it last week. Okay. So the proofs is really very simple. We don't even call it a theorem, we call it a proposition. So the claim is that up to isomorphism, admissible graph homomorphism, and I hope it's obvious what I mean by isomorphism. It's isomorphism between morphisms. So I say that two morphisms are isomorphic if I have an intertwining isomorphisms of graphs. Okay, and that's the obvious definition. I didn't bother to write it down. Okay, so up to isomorphism, all admissible graph homomorphisms into a given graph E. So this is fixed. I take a graph E and I'm classifying all admissible graph homomorphisms into this graph E. So if you want, I want to see how I can contravariantly derive all possible equivalent star homomorphisms from graph sister algebra of E to graph sister algebra of something else. Okay, and so first I have to have a proper map from the set of vertices E by 0 to E0. And now it has to satisfy this weird looking condition. But if you look at this condition of what it actually means, this is a condition that is necessary and sufficient for S-pi to exist. And we must have a commutative diagram here, right? So when I take pi1 and compose it with SE, for this to be commutative, of course, the image of this composed map must be contained in the image of pi0, right? But now remember, this is a pullback diagram. The right one is a pullback diagram. So you know exactly what is the image of pi1, right? These are all edges, okay, which are compatible with some vertices. But when does it happen? I take my edge, I take its endpoint, and it must be the image of pi0. Otherwise, it will not be a compatible pair. It will not be in my pullback. It will not be in my fiber product. Okay. So therefore, you see that what is written here, that's just the image of pi1, and then I apply SE to this. Okay. So this is the image of this composed map, and the image of this composed map. Sorry, there's the same here and there. The image of this composed map must be inside the image of pi0. Otherwise, I will not have S-pi. I will not be able to have a commutative diagram. Okay, but the moment this condition is satisfied, I can have a partial splitting on this set. Okay, it's just axiom of choice. Yeah, because this is contained in the image of pi naught. I can always choose S naught such that pi0 composed with 0 is equal to identity. Okay, and now I'm left with one and only one condition, which is the regularity condition. So if you really want to axiomatically define what are admissible graph homomorphisms, then the first condition of the divisibility is properness, and this is what allows you to have a homomorphism between path algebras, and you need properness in order for these sums to be finite. And by the pullback property, pi0 is proper, so is pi1. So the sum is always finite. And next, you must have the second condition is this target bijectivity condition. But target bijectivity condition means the Cartesian square, and this is already built in here, right? Because this set of edges was defined as a fiber product. So the second condition of admissibility is built into the structure. So there's only one condition of which you still have to take care of, the regularity condition, which is responsible for preserving the second Gunst-Krüger relation. And in the contravariant case, in the case of graph homomorphisms, unlike in the case of path homomorphisms, the regularity is very simple. You just say that preimage of regular vertices is regular. Oops. Yeah, it's very simple. But now, if you in fact remember that the map pi0 is proper, it's obvious that in the preimage of a regular vertex you cannot have any infinite emitters. So basically, all that you are saying is that the preimage of a regular vertex cannot be a sink. Okay, and it's not a sink if it's in the image of a spy. But what is a spy? It's the composition of SE and S0, and this is just the image of pi1. Okay, so this is the regularity condition. And that's it. So you just have two maps. You have a set theoretical map satisfying this condition. When this condition is satisfied, a splitting exists, okay? But the splitting must corroborate with pi naught in such a way that this condition is satisfied. And we made some experiments with Elizabeth, so it might happen that you have pi naught, which is subjective, so this condition is satisfied, you have a splitting, but there's no splitting such that this condition is satisfied. So you cannot read this condition as a condition on S naught alone. It is a package, it's a condition on both S naught and pi naught. Okay?
You can actually draw the graphs too.
Yeah, can you do it? Yes.
Yeah.
Thank you, Liz.
Okay,
This is wonderful.
fun with MS Paint. Those skills are coming in handy. Okay, so I'll draw the first example, which was, let me think.
Fruitox 1.
Well, I mean, this is a superposition. I'm helping her with her talk, she's helping me.
Okay, there's one set and then.
Yeah. Yeah, so this example shows that this condition is not vacuous. Because for starters, you could think that, okay, if you sort of shrink the image of pi naught, okay, you also shrink this one. So you could say, well, maybe it's always satisfied, but it isn't. Here I have a counterexample. If you look at it as your e pi, yeah, this is e pi.
No, the top is E pi, I thought, and then you.
No, it should be injective, not subjective. So this is e pi, this is e.
Oh.
So if this is e pi, this is e, and you can quickly explain what happens when you see that this condition is violated. So such S pi does not exist. Yeah. So this is not a vacuous condition, but that's kind of obvious. Well, this is even more obvious. However, that's important, right? If you have the following situations of here, this is e pi, this is e. Here you are subjective because you basically identify these two vertices, okay, and this sink goes to this sink. So pi naught is subjective, so this is satisfied and S naught exists. But whichever S naught you take, and the only S naught, we have just two possibilities. This must go to here, but this source here can go to a sink or it can go to this source, okay? But whichever of these splittings you take, you see that this condition is violated. And indeed, this doesn't work because here what happens that in the preimage of a regular vertex, you have a sink. That's not allowed. And if you look in terms of graph system algebras, you cannot have a unital star homomorphism from 2x2 matrices into 2x2 matrices plus complex numbers. It does not exist. So basically just to make a point that this condition is not a condition on S naught alone. It's a condition on both pi naught and S naught. Okay. Now again, yeah, but it's somehow drawing disables clicks.
Yeah, and then if you have the red X at the bottom, you should have that control with the arrows, I think.
Okay. Yeah, after click, right? And now with this classifying datum, we obtain an admissible standard graph homomorphism simply by taking S pi to be the composition of pi 1, SE, and S naught, right? And this is completely obvious what happens. Look at this diagram. If I want to have the S pi, I go down, I go left, and then I split pi naught, right? But I have to be able to split it. So for me, this is remarkably simple because whatever you look at, I mean, for already decades, you have a theory of admissible subgraphs. This is in books. It's been used over and over again. Now you have outsplits, right? So you have something which is subjective, but not injective. Then you have Stallings moves. You have many things, and all of them are admissible graph homomorphisms. So it looked like something very big. We have derived graphs. We have locally derived graphs. There are really many examples that you can cook up. So I was, to be honest, quite surprised to see that all this apparent diversity and variety of examples boils down just to a set theoretical map with some properties and it's split. That's it. Up to isomorphism. Okay. So as I told you, what Tomasz wrote as a theorem, I write as a definition. So again, it's not like Tomasz worked with the Teresa Bates and David Pask, but that's exactly this definition, which we got from him. So we take a subjective admissible standard graph homomorphism, satisfying this extra condition. And this is, Tomasz, I believe this is what you say is bijectivity on things and bijectivity on infinite emitters. Okay, I believe you can nail it out just to this. And you have the source splitting. I like this. Yeah, source splitting is a very good term. I think we can add it into our paper, call it source splitting. Yeah. Rendering the following diagram commutative. So this is exactly what we had in Tomasz's talk. And if a graph isomorphic, if a graph homomorphism is isomorphic to pi, we call it an outsplit homomorphism. Okay. So if you want, this is a standard form of an outsplit homomorphism. But you can, of course, mess it around a little bit by twisting things by isomorphisms of graphs. And a little bit more of terminology, because I started learning about outsplits from the paper of Soren and Effen, and they just outsplit the vertex, unlike Bates and Pask. Then if you want to outsplit the vertex, well, basically what you have to say that if you take any vertex that is different from W, then in the preimage you have only one vertex. So we are basically injective over there. So there's no outsplit happening at other vertex than W. And you also have a very useful concept of a maximal outsplit, which can happen only at a regular vertex. But again, you can phrase it in terms of a source splitting. Okay, basically, what you do, you restrict your source splitting to the preimage of the source preimage of a regular vertex. Okay, you restrict your source splitting to the source preimage of a regular vertex as a finite set, and then you demand it to be injective, and that's exactly the maximal outsplit. Okay, I like it very much, but you can say it in terms of a source split. Okay. Yeah, and it's very easy to check that every outsplit graph homomorphism is a surjective admissible graph homomorphism. So, because we know that any admissible graph homomorphism contravariantly induces a star homomorphism, U1 equivalent star homomorphism between U1 graph hysteralgebras. Well, in particular, so does this one. And this is a very simple fact. It's really not a big deal to prove it. Okay, it's surjective by construction, and admissibility is basically what it's immediate, because I have this classification which is given earlier on. So basically, it's like what I have in my previous slide, but in addition, I demand surjectivity of pi naught and existing of the source outsplit. So I'm just specifying what I have in my previous example. Okay. And this is what Elizabeth calls the Mickey Mouse graph. I like it. It's the Mickey Mouse graph. This is a Hawaiian earring, okay, or rose petals. And here you can see this S prime in action. Okay, so I have a maximal outsplit of this graph. Okay, I choose my vertex map pi naught to be given here. So I have the vertices V1, V2 mapped into V. So this is my set E pi 0. Okay. Now I have this pullback construction. So because here I have 2 edges and I have 2 vertices, obviously here I have to have 4 edges, because I will have to look at all compatible pairs, right? Now, if you want in my new graph, the definition of vertices will be given by pairs. I have E combined with a vertex Vi, I'll have F combined with vertex Vi, and okay, I will run 1 and 2. And of course, everything is compatible because here we are subjected not to V. And by construction, the end of EI is exactly the vertex VI. Now when you want to see the source of your edge, well, then you have to use your source splitting. And the source splitting is very simple. I assign to EV1 and I assign to FV2. Okay. So when I do it, I know already what is my S pi, because if you look into this defining diagram, my S pi is the composition of the canonical projection of the first component with S prime. So I take such a pair, right? I take a pair EVI, I subject into E, and then I use this splitting. So if I look at S pi of EI, it must be EV1, and if I look at S pi of Fi, it must be V2, and this is exactly what happens here, and that's this diagram. Okay, so this is a very simple exemplification of that definition. Okay, so now, and this is the last slide. So I'm very fast because
No worries.
Yeah,
I'm very relaxed.
we are.
Our talks complement each other well, so I'm not feeling stressed about time.
Look, there's a very funny effect. In general, the composition of outsplit graph homomorphism is not an outsplit graph homomorphism, as Tomasz emphasized. This is why he went into hypercategories. But we don't care about being close under the composition in terms of outsplits, because we have the ambient category where we live. And an example here is you take the Teplitz graph. Can you draw it? So
Didn't realize
from Teplitz graph.
I had no idea my MS Paint skills would be so useful in my future life. Okay.
So a Teplitz graph, yes. And then you outsplit it once.
Oh, okay. Let's see. You're just going to imagine the arrow to the side.
Yes, so that'll be two arrows.
Mm. Mm.
And you outsplit it again, and there will be 3 arrows.
Okay, I can do that, but I'm not going to do 4.
No, there's no more space.
Let's see. Mm. 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 Mm.
Wonderful, thank you so much. So you see, you take the Teplitz graph, there's only one non-trivial way to outsplit it, and this is when you get this graph. This graph you can again outsplit in only one way, you get this one, but this graph here is not an outsplit of this. Okay, so you cannot compose outsplits, okay? However, you have a very beautiful and important I cannot say 2 out of 3 because it's not for any 2 out of 3. This is why I call it the factorization property. And this works in the following way. Imagine that you have 2 outsplit graph homomorphisms. One is pi, one is tau. Okay, and also imagine that you can factorize. That you can factorize via a subjective graph homomorphism. I don't even claim it's. I don't even assume it's admissible. Just subjective graph homomorphism, which goes from e pi to e tau. So in other words, I want to factorize my pi via going by rho first and then coming back by tau. Okay. If I have such a factorization where I assume about rho only that it is subjective graph homomorphism, okay, whereas I assume about tau and pi that they are outsplits. Then I can prove that rho is also an outsplit. Okay, and this is an extremely useful property that we need later on for our main results. So we didn't do it just for the sake of doing it, or for some abstract reasons. We really needed it in our calculations. Okay, because the main game of what we are doing in our joint work is to write combinatorial formulas for the inverses given by moves, not for the star homomorphisms given by moves, but for the inverses. And then we have to use adjuncts of generators. We have to go to extended graph homomorphism. It's a bit complicated, but this is not the subject of my talk today. Yeah. So you have this a nice property, and I must say that this is at this proposition, which is important for us, where this Tomasz's formulation of Bates-Pascal split is wonderful, because it's so much easier. I mean, that's not a trivial proposition. It's like a page-long proof, okay? And it probably would be a nightmare proving it using this cooking recipe of Bates and Pascal, using source splitting and maps and diagrams. allows us to prove this proposition within just one page. And this is, if you want, our immediate application of this form of looking at an outsplit. This is why we adopted it. And to end with, I just want to tell you that this is in contradistinction. I love this word, contradistinction. This is in contradistinction to what happens for general admissible graph homomorphisms. Because of course, general admissible graph homomorphisms are admissible, they form a category, so they're composable by design, but we do not have the above factorization property. And let me give you an example, and this will end my talk. Okay. Elizabeth, if I will struggle, I'll ask you for help, but let me try. Okay, I start with the same graph as before. So I have one sink and one arrow. And here I have an arrow and infinitely many arrows here. Okay. Thank you. So I have the obvious map. I map this base arrow to the base arrow. Okay. I identify this sink with the beginning of this arrow, so it goes to this vertex in here. Okay. And you can check that this is an admissible graph homomorphism. Okay. In particular, regularity condition is satisfied because the preimage of regular vertex has to be regular vertex, except here there are no regular vertices. You have two sinks and one infinite emitter. So everything works. Okay, you have no problem. Such a map exists. But now, if you think naively, all right, so let's take the image of this graph, right? I take the image of this graph, and the image of the graph is very simple because I identify this floating sink with the source of my unique arrow. Okay, so this is the image. And you can check, it's no problem, but this is an admissible inclusion. Okay, this is an admissible inclusion. Which can very easily imagine, because if you outsplit at this vertex, then you'll have a direct sum of 2x2 matrices and minimalization of compact operators, and then you just project out minimalization of compact operators at a unital homomorphism. Okay, it's not a big deal. So the total arrow is admissible. The last arrow is not admissible, but the first arrow is not admissible. Okay. Because here you have a preimage of a regular vertex which has a sink. So this factorization property is not enjoyed by general graph homomorphism. Of course, for outsplits, we do away with this problem because outsplits are subjective. And here, you know, the reason why we have this counterexample is because our admissible graph homomorphism was not subjective. And I think I will stop at this moment and pass it to Elizabeth. Thank you, guys.
I will go back to Tomac's using of the board because that's what I had ready. Let's see. And I guess actually I will maybe stop sharing here. And then I look.
40 minutes. That's very good.
Oh God. There we go. That's about as good as I can manage. This. A new page all ready to go. Thank you. Okay, so to exactly leave the very convenient cliffhanger that was left. What about admissible path homomorphism? It has a lot of the same ingredients, but something new. So I'll actually choose them on this. Okay, so we'll have F. This is not thick enough. Let me. And let me check.
Yeah.
Yeah, that'll work. F. Finite paths in the graph E, and finite paths in the graph F. Okay, and these conditions that I'm writing are enjoyed by both. They were already mentioned, but I think it's worth reminding us that this late hour. Vertices map into vertices. Source and targets are respected. You take the source of in E, you then go with F, same as if you go over with F, and then the same thing with the target maps of F composed with T, E, okay. And then it respects composition. So for all P, Q in the source, if you map them over, you can distribute F. Okay, none of this is surprising. You've seen this before. Old hat. I'm boring you to tears. Oh, also monotonic, which is F, if FE is comparable, let me maybe erase that. That was not as, we use fancy less than or equal to because the other less than or equal to is already busy. If you map two things over and they are comparable, which remember means that the image of this is some path, the image of this is some path, and one strictly extends the other to the right.
But you have to say that E and E prime are edges, otherwise.
Oh, yeah, sorry.
See, our initial condition was for paths, that we have alpha prime, and then we said, aha, if f of alpha is extended by f of alpha prime, then alpha is extended by alpha prime. And this is too restrictive. This is more general.
And then, so what is new regularity? T, oh God.
And this is more general because you can map an edge, a loop, you can map it into a vertex. Then see that the previous condition is too restrictive.
Okay. Anticipation. What the hell was that? Okay. So for all B, so I'm going to write out a longer definition, and then there's a shorter definition that parses it well, but it might be worthwhile to think about the longer definition, not only because that's how it came up, but it might help break it down. So for all B in regular vertices of E minus these zero regular vertices. What are those? I will totally come back to that, but let me leave you hanging on that for just a moment. Okay, so F. Okay, I am writing F restricted to S inverse. Oh, sorry. Sorry, I'll erase. Okay. So let this be something in the image of, it's the image of an edge emanating from a regular vertex. Okay. Strictly positive length n. You're not mapping edges to vertices. You're mapping them possibly to longer thing, but strictly longer guys. Maybe to edges, but anyway, you have this. You also have that if this is in your image, sorry, not F inverse, inverse in wrong location. Okay. Sorry, T F of, yes. Okay, so what this means is if you have think of, like where you're comparing two different images, you have edges and you're mapping them forward, and this condition would be saying that their images are comparable. If you could write this PQ business, and this is saying actually they would really be the same. Like if one has P as an image, one has PQ as an image, that they're secretly the same thing.
So in other words, when you have a path in your image, neither a subpath nor the superpath can be.
Yes. So each edge go to non-comparable paths.
Exactly.
Okay. And then this one's a little bit harder for all I in 1 n, specifically that n. Let's see, and E in S inverse. So this is in the target, S inverse F, S of EI. This EI coming from here. So we're in this remember is in the image. So we're at here and then what they're at the target of one of these EIs in the image. That is an F, believe it or not. Okay. There exists R and let's see, F, P, F. Actually, that E1, EI, E. So I'm going to underline that just to remind you that that's new. R is in F of S. Okay. This is probably the weirdest one to talk through, but let's go through it slowly. So you have some path in the image of some arrow emanating from a regular vertex. And it just so happens that if you slice that off somewhere else and you choose any edge in the image that emanates from there, you can find that maybe plus some additional junk in the image of, it's still in the image of arrows emanating from this regular vertex. So as stated here, different edges will not be comparable. Yes. But this, it says that anything you think of in the image, you can compare it to something. Yes. So that's what's going on here. Things aren't comparable to each other, but they are comparable to everything. Okay. So that's, oh yes, and then I owe you this. I owe you this.
You can also, put it in this way, that once you are building your path that is in the image of F, but it must have this property that at a certain moment, when you're making the next step, adding another edge, you must satisfy this property that if at this vertex you choose any other edge, then possibly with some extension, you'll get something which is also in there. So if you want, the rule of thumb is that if you extend your path to a longer path, you must extend it in all possible ways. And this is precisely because this is the only way to have the consquare relation to satisfy. Because what we want to have at the end of the day, this is a regular vertex, so we have a second consquare relation. So we have a sum of E star is equal to a vertex. Now I map it over there, and I have sum of alpha alpha star is equal to the F of D, this new vertex. But now alpha alpha stars are paths of different lengths, okay? And in order to somehow use the consquare relation on the other side, you must have this extension property. Yeah.
Okay, zero regular vertices are vertices who knows what's incoming, but the only thing they admit is one loop. Yeah. So the complete set of all arrows emanated from that V is E, and the target of that E is V. So those are guys that you can do crueler things to, and those crueler things is that for here, it is actually safe to map this edge in particular to the vertex. Yeah. So you can do the same business with this, or you can choose to just crush it to death. Yes. And send it to the vertex.
And if you want to, in terms of your sister algebra, what we are saying is that, okay, you now have a partial unitary because you have E star equals to projections and E star is equal to the same projection. So this is like a partial unitary. And a partial unitary, of course, you can squash it to the projection without killing much of your sister algebra.
Okay, so then I'll state this in the shorter way, and I will see how 0. Okay, absolutely 0. We can also say F. Okay. F S inverse B of B, where B is a regular vertex, we're not doing anything weird, is an orthogonal cover.
cover F of V.
Remember that vertices are still mapped to vertices. So this is some vertex in F. And what it means to be an orthogonal cover of F is any V, F of V, path in F extending from F of V. It is comparable to something in this set. It maybe extends something here. It is maybe initial segment of something here, but any path you have in your image is comparable to something here. Okay, so that was the shorter way of saying it, but it was worth it to parse it, I think, in the longer way that both it came to be and that it was understood. Okay, now in the 0 time I have left, I will very briefly show you shift out. Unital reduction might have to just go out the window. Okay.
No, we go back to that class.
Okay, so you aren't prisoners.
Yes.
Enjoy your time. Okay, so let me first show you the path homomorphism that meets all the conditions that have been written that describes the shift. And maybe I'll first draw a little cartoon of the shift, and I will try to be mindful that we are pumpkining as we speak. Okay, so the input for shift is this. You have V. V is regular. You demand that. He's admitting only finitely many vertices. Sorry, he's admitting only finitely many arrows, and he's not a sink. You have W over here. W can be an infinite emitter. It cannot be a sink because of the next thing I'm going to state. So V admits so many arrows. Honestly, can even emit a loop. Why not? Okay, and W, it will also emit arrows. And maybe I'm going to be bold. Ah,
Wow.
yes.
Crimson.
And I'll switch back to white. And just to satisfy the audience, you know, sure, infinitely many guys, whatever. Okay.
Countably many.
So the point is that W must have arrows emanating. Oh, sorry, there's one more. Yep. I see it.
To the loop, you have a loop.
There we go. Okay, so I look at the targets of arrows emanating from V. And those that's a subset of the target of arrows emanating from W, but in such a way that I can match these up bijectively. So in particular, like there you have one choice of bijection, like I didn't give you much room, like this is matched to this. Wow, this is matched to this. This is matched to this, and this is matched to that. And we describe this map with theta. Theta.
Now it looks like a funny face.
Yes, it does. Theta is a map from S inverse of V, and it injects into, not necessarily the whole thing, clearly this has more stuff, S inverse. I get to experience your frustration. Why is it moving on me? S inverse of W. Okay, so this is our original graph. We have regular V, whatever the hell's going on with W, and we have this data. That's our data. What do? Our new graph will be this. We'll change back to white because I liked it. Okay, so V continues doing what it was doing before, but W has radically changed. W, okay, it still has this guy, but all these matched arrows to arrows in V are gone, erased, eroded.
Forgot.
Yes, and because I did have fun with it, I will choose blue.
Wow. You ended with
yeah.
a green edge. How did you do it?
Okay, you erase all your old edges that emanated from W that were matched with arrows from V. So in particular, you erase the image of theta and you replace it all with a superhighway. So what you should think of is that previously in your old graph, you would have gone like this. Now they've destroyed your road, bastards. So you go like this.
It's a detour.
You go with superhighway from W to V with handy subscript. And then you go with the arrow that was matched, because in particular, I think it was clear in the picture, but I'll state it now just to be sure. Theta respects the target. The target of this is the same as the target of that. That was the only information you needed. Okay, so what the hell is the path morphism? Honestly, probably you guys could do a decent job of writing it down. It is, so.
Wow, this is interesting. Why does it happen?
Okay. So I think it's my shirt. That's what's happening. Was it your shirt too?
No.
Okay, so F of, and see, here's where I satisfy my audience, because you care about this S of E. I would just put E. But here, this is an element of the graph C star algebra. Actually, okay, so no. I'll first, yeah.
Let me know graph is the same.
Okay, but in particular, if I'm doing that, so F, just in case you read the paper and you're like, what the heck's going on? F would be the map from the paths in here to the paths in here. F sub star is the map between the algebras, but it's basically the same thing. Okay, so
And here, let me more general system.
in E1, in E0, oh, well, sorry, no, wrong. Running out of space. 0, 1 minus theta of S inverse of V. Okay, so notice that for the white arrows here, nothing changed. I map those things to themselves. Okay, then for here, these guys, what I map them to is S of X W V theta. Oh, sorry, no, wow, too large. S sub theta of Y, and this is, sorry, I have to put it down here, or
Plus.
okay, for Y in theta of S inverse. Oh, sorry, for theta. These were the arrows that were previously emanating from W. And yes. Okay, so this is exactly this arrow in the image of theta being replaced with this arrow. This arrow was previously matched up with this arrow. It ends in the same location. So if we think back through our previous conditions, vertices are mapping to vertices. In fact, pretty much like if in some blurring of language, the same vertices, the same freaking vertices. And then source and target map are respected. Like these conditions are the ones that are not too bad. I guess maybe we could focus momentarily on this. Like the only way that edges are comparable is if they're the exact same thing, because they map to pretty much themselves. Like they had to be either the same arrow, or in this case, they would be distinguished by this theta of Y. Remember, this theta of Y is theta is an injection. And then it's just checking this, that in particular, okay, so I have arrows, they map to paths of positive length. Yes, they all map to guys that are 1, or they map to paths of length 2. Sweet. And nothing in the image of any 2 arrows is comparable. That's kind of like, actually, I think this might be free from monotonicity. Okay, but no matter what path you give me, so if you give me a vertex, whichever one you choose, you give me a path, you give me a vertex, you give me, honestly, any path in here, it is comparable to something here. So the only thing that you really have to check is, for instance, at W, you've clearly changed things with this X sub WV, but so the image of things here is X sub WV theta sub Y. But remember, V was a regular vertex, and we did this pairing for all the guys. So no matter, even if you're looking at just the path X sub WV, that is comparable to these guys. If you're looking at anything X sub WV, whatever else way you went, yes, that is still comparable to something here, because this covered all the arrows emanating from V.
Or to put it differently, if you look at the superhighway blue arrow, you extend it by all edges emanating from it.
Yes,
That's the point.
yes.
This is why constrictor
double.
two is sums.
Okay, so then what is,
So if you want to have just a path homomorphism, then you have E going to E if it's not in the image of theta, and then you are mapping all Y into the path, which if you want is given by the subscripts of S's. And when you use the formula for this covariant induction, and you have a star homomorphism.
it's great.
Now, while you write, let me say it, because we're really a bit flabbergasted with Elizabeth that nobody bothers to write a formula for the inverse. So first, originally we learned about shift from a paper of Abrams, and he uses a bunch of completely irrelevant assumptions, totally completely irrelevant assumptions to say that he has an isomorphism. Then you go into Ayers and Ruiz. They do it terms of unital reductions, but again, they don't bother to have the inverse formula. Whereas here, this is absolutely amazing, because you have a totally conspicuously obvious inverse formula, because the only thing that you have to figure out, if you look at the formula above for F star itself, okay, the only thing that you have to figure out is why on earth this is subjective. How can I get S theta Y? How can I get SX WD in the image? And when you answer this question, you have a formula for the inverse. And because it's not written in the literature anywhere, we proved it with Elizabeth right now. We just verified it, but this was like a high school exercise. Everything works. I mean, you just check that constrictor relations are satisfied, so you have a well-defined star homomorphism, and it's completely obvious that these two formulas are mutually inverse. So why nobody wrote it?
So
It's-
with this fantastic typesetting, I'll briefly recount the map backwards. So on the set of the white arrows, it's the same. Wow, you're at home already without even realizing. For the one case that is different, so this is going backwards. So this is the one really new thing that goes backwards to this sum. So this also brings up something cool, that for admissible path homomorphisms, you do get an induced C star / Leavitt homomorphism. This happens to be an isomorphism, but its inverse in particular is not that way, mainly because of this guy. Look at that sum. That is not something we have with when we define F going from paths to paths. We don't have sums of paths. So
And also not the adjuncts. This is very
yes, also that, but also not sums. Both.
Yeah,
Two
yeah.
problems at once. Okay, so yeah, it's very easy to napkin check that, like, this respects Kunstkrieger 1, this respects Kunstkrieger 2, this is the inverse, irrespective
And
of
for
the
other
one.
reasons, why nobody wrote it down for 20 years?
I mean, if you can find it, please let us know. Because I don't want to miss giving credit where it is due. But yeah, this is, I can say in all honesty, not that smart. Like,
No,
I'm not
it's
a genius.
kind of ridiculous proving it, because it's just an exercise.
I thought I don't know, like, yeah. Anyway, so that's what's going on with shift and the inverse of shift. This is induced by a admissible path homomorphism. This is not, but they exist. That's why going to the category is so important, because you have nice combinatorial conditions on the previous things that I will not scroll to that give you this. And then this just happens to exist ambiently in your category. It's kind of cool. Okay, unital reduction.
Yeah.
Okay, so
So shifts come from people
Leavitt.
who Leavitt, and unital reductions come from people who do graph system algebras.
and Leavitt. I believe it was known to both, actually.
Okay.
Okay. Well, mainly, I think I remember my advisor told me he had talked to Soren or something, and they agreed that they had kind of come up with the same thing, but my advisor's formulation of it involved the source that you add in unital reduction, which you're about to see momentarily. If you do a maximal outsplit on that, that would be what. So I think both people, it's like at the top of the Tower of Babel. Like, I think these are, anyway. Okay, unital reduction. You have, again, B. B is regular. You cannot escape that. B admits finitely many guys, but it could actually be an infinite receiver, but I'm not going to draw.
Could be, yes.
Yeah. So we have that. Oh God, that was a mistake. Okay. So, oh, sorry, regular, and there's one other thing. Classically emits no loops.
Which is a redundant assumption.
Well, hope kills. We hope. But
I
okay.
think I would bet 100,000 euros.
I'm not a gambling person. Okay, so what you do with unital reduction is this. All paths of length 2 through V, which you don't have to worry in this particular setup of getting caught up in loops, you replace those paths of length 2 with arrows. So in this particular case, I should not have chosen 3, but that's fine. This is 2 times 3 is in fact 6. Yay. But you also remember, so there is a map that is reduction, which is just like, that's it. You're done.
Now I'm already.
Yes. Yes, but if you do unital reduction, you get a Leavitt path algebra isomorphism. So you remember the ghost of this.
Yeah.
So like I drew the kind of the copy of V up here because it would have gotten way too messy, but still all of its outcoming arrows are reproduced.
So another way to put it is that you look at all these incoming arrows in V, and you replace them by paths of length 2. And you replace them by edges which now end not in V, but which end at the other endpoint, and you have as many such edges as you have paths of length 2.
Okay, so here, just to clarify the direction of things, this is ER plus for unital reduction. This is E, and our map is going to go from ER plus to E. So actually, you know what, let me write the classical F. So no substars, F. We're working on regular guys. And F equals E, as long as E is in here, I'm going to do something that feels awkward. So I'm going to toss vertices in there as well. But so it's in E0 square E1, but minus arrows that ended at it. So target inverse in E of B. Let's see. Wait. Hang on. Sorry, because I'm starting from here. So
Yeah, I mean.
yes. That's fine. And then I believe that's yes, because those arrows are perfectly matched up. And then E F. If let's see, or so let me decorate these in a way that it makes sense. Here, let's say this is an incoming edge E, this is an outgoing edge F. So those edges, this path of length 2 was replaced with a single edge. I will give it the label EF. Okay, so to reiterate what the heck is happening here, almost everything goes to itself, including this V goes to that V. These outgoing arrows go to these outgoing arrows. So it works on everything except those edges that were coming into V originally.
So then it's a map from E to ER plus.
No, it's the other way around. It must be a map from ER.
Yes, it's a map from here
But
to here.
then E goes to where?
The labels are the same. So in particular, EF, this for instance would also have label F. This has label V, this has label V. This has, you know, this is W, let's say, this is W. So
Where is E in ER plus?
where is E in?
I
I should-
This is now a new vertex. It's now replaced by.
I am grossly identifying some of these sets, which is probably very confusing. But for instance, the vertex set here is the same as the vertex set here, yes? And the arrow set here, a lot of it is in perfect correspondence with the arrow set here, with the exception of the arrows that were coming into V. The arrows that were going out of V, they're actually still perfectly matched up here. The arrows that are outside here in the vast blue yonder distance, they're fine. We're not touching them, so we're keeping their labels exactly the same. But the arrows that we don't have in this graph,
would be exactly arrows perfectly corresponding to these. What we instead have are arrows like this that correspond to paths of length 2. And to those guys, I map them to the product. I mapped this edge EF to the path EF.
Yes, because you see, the unit of reduction is simply the inverse move of a shift. And the homomorphism is always going into the same direction. Okay. Yeah, it's always come out, exactly.
Okay, so yeah, to explain what is being said with that, here I'll give you the definite case where I will stand on a soapbox and say, yes, they are definitely inverse. If I started with this graph, let's say, and I did unital reduction.
So unital reduction, but in the case where your regular vertex V receives one and only one edge.
Yes. I've tried to make this somewhat three-dimensional in a way, but this is the guy that I did the reduction in. I kind of like to lift it above, and we see still the arrows coming out from it. And these two paths of length 2 were replaced with two paths of length. These two paths of length 2 were replaced with single arrows, still emanating from the same guy. And then if to this I do shift, which now has actiony green colors. Oh God. Then I look at the input for shift is I have two vertices where the targets of the arrows emanating from them are, one is at least contained in the other. In this case, they're exactly the same. Woohoo. Okay, so then what I do is I choose to erase the arrows emanating from W, and then I draw a superhighway there. So just to try to keep our perspective the same.
And lo and behold, it's the same graphics path.
So in this particular case where I've made some pretty bold assumptions, like for instance, here, I only had one incoming arrow. And then, yes, but with unital reduction and shift, I get back. But we hope, but hope kills, but we hope that maybe the data of shift and the data of unital reduction could be expanded to where they're more truly inverse of each other.
I think it's more than a hope. It's a proof that requires double checking.
Why is this called shift?
And so I was guessing because, I mean, you shift from here to here. I'm not sure if that's really, if that feels shifty.
It's aberrant. If you want to blame anybody, it's aberrant. Elizabeth,
Where did it come from? Simple dynamics.
Maybe. This I don't know, to be honest.
I don't.
It's a good
I'm not
question,
sure.
maybe. I know that outspeeds definitely come from symbolic dynamics.
Yes.
I don't know about shifts.
The completion theorem that.
Elizabeth came to this one more exercise when we start with a shift,
Okay.
but a shift at the source and without loops.
Okay, so source, I like this blue color with no loops.
Yeah.
And then I have other guys doing this.
Exactly.
Okay, and then you want me to shift.
I
Okay.
want you to shift.
All right. Shift. I can match these up either ways, but I'll have this be the guy that is my regular vertex that is preserved. This is the guy where I erase from, and I match up in the only way that I'm allowed to match up. I mean, what do you want me to do? Okay, so shift, and then you want me to do unital reduction.
And I want you to do it over that.
Okay. Unital reduction. Okay, so unital reduction, I do it at the regular V.
Yep.
It supports no loops, and that will give me, so da, 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 da. And very conveniently, my V is already up here. Oh God.
Sleeves.
Behold, the same.
Okay.
But keep in mind, with shift you can, so the difference in data is that for shift in particular, including my example that I drew up, you can have V is a regular vertex, but it can support a loop. So that part needs to be generalized in order
It
to
also
have.
need not be a source.
Yes, it also need not be a source, but so that part has to be safely generalized. There's also when you do unital reduction, you consider for a regular V that doesn't support a loop, you consider all incoming arrows and all paths of length through length 2, starting at a vertex different from V, in part because it doesn't support a loop, that go through this. And so part of the ways that we are hoping that it can be generalized is that for shift, when you choose your data of 2 vertices, like why limit yourself to 2? Why not do it for a bunch of guys? Like the outsplit generalization. You don't have to outsplit at 1 vertex. You can outsplit at many vertices. You would have a bunch of betas matching them up, but you can do that. And similarly for this, we need to be careful with loops, but maybe we can just allow loops and specify that paths of length 2 have to start outside, they have to not be V, they have to be something else. And then why do all W? Like, why do everything that's coming in? Maybe just a subset. And then that would be, you'd have a subset of guys that you're shifting from, a subset of guys that you're doing this unital construction with.
I can
Maybe.
explain how we do it.
And that is, I'm how far over time am I? Yeah. Yeah.
But can I
done.
just explain how we do
Okay.
it in general? It will be 2 minutes. Okay. So what Elizabeth showed is that under these additional assumptions, these moves are really mutually inverse. Okay. If I take a shift at the source without a loop, and then when I obtain a graph which has a regular vertex admitting only one edge, and then I do unitary reduction at this, and I come back to the original graph. It's a mutually inverse procedure. Okay. But now, I mean, things work in full generality, whether I take unitary reduction or take a shift, I always have a star isomorphism. So why not combine these 2 languages? How to enlarge the definition of a shift and enlarge the definition of the unitary reduction such that in full generality they are mutually inverse. Okay. So at this moment, maybe not. Where are these colors here, right? Okay, let me go back to white. Okay, so we are in this situation that we have an intersection here. We have shifts, here have unitary reductions, and they're just mutually inverse to themselves under some assumptions, which means they give you exactly the same path homomorphism, admissible path homomorphisms. Okay, but there's no reason to do these assumptions. It's just a reason to somehow reformulate your cooking recipe for a shift and reformulate your cooking recipe for a unitary reduction. And I agree, it requires double checking, but it's much more than a hope. It's basically a sketch of a proof. So for the unitary reduction, we do the following. We take one vertex V, that is true, this remains same. It can have a loop, but it's a regular vertex over it. Okay? But now instead of taking a vertex W, which is different from V, you take a set of vertices V, a W, such that V is not in W. Okay, this is important. But the set can be as large as you want. It can be uncountable. And now you do the same procedure that you did before, but now for each separate vertex W. And there's one more twist that you have to account for. For every W, you have a family of theta's. Okay, because it might happen that you have this vertex lowercase w in the capital W, and say it emits 20 sets of n tuples which match. And so you can have, for each vertex W, you can have as many theta's if you want, even uncountable many. You can have it, it's allowed. Okay. The only thing is that of course, you assume that the images of theta must be disjoint. Okay. So not only that you can do it at as many vertices as you want, but for each vertex you can have as many theta's as you want, which preserves the target and biject. Okay. So this is how we want to generalize shift. And our formula for the admissible path homomorphism and inverse is basically identical. Just have to do some declarations. Okay. And now how about the unitary reduction picture? Okay. So for starters, really, there is no reason to assume that this regular vertex admits no loop. Why not? It can have a loop. Okay. And now the problem is that you have here as many incoming edges as you want. So what would be the recipe for unital reduction. So for starters, in order to avoid producing a source, you don't have to change all of these incoming edges into paths of length 2. You can say that you choose a subset of these incoming edges. Some of them you keep, and they remain as they are, and other ones are removed and replaced by edges which coincide with appropriate paths of length 2. And when you write this recipe, you see, in order to take care of a loop, because they say, hey, a loop is also an edge which comes into this vertex. Well, you must really look at edges that come to this regular vertex V from another vertex. They cannot come from the same vertex. So this loop is not counted as an incoming edge to this regular vertex. And that's it. This is a unital reduction, which is perfectly inverse to this one. And you should have a admissible path homomorphism, which gives you an isomorphism of graph hysteroalgebras. And now I think we really end. So thank you very much, guys. High five.
Thank you for your patience. I tried to shape it down.
You are great. This was a fantastic talk. Yeah.